A block of grey sandstone the size of a car door lies broken open on the beach at Howick Bay, on the northeast coast of England. It fell from the cliff in a January storm in 2018, and the sea has already begun to work at its edges. The tide washes over it and pulls back, and there, along the freshly split face of the rock, runs something that does not belong to any ordinary stone. Curved plates, overlapping ridges, row after row of tile-like armour segments, stacked the way roof tiles stack down a slope, larger than any arthropod anyone had ever pulled from British rock. For a while it is just a strange pattern in a fallen block, cold and wet under a northern sky. Then the fossil hunters arrive, and the measuring begins, and the numbers that come back are difficult to hold in the mind. The animal these plates came from was about 8.6 feet long, almost 2 feet wide across the back. It weighed something close to 110 pounds. That is the length of a small rowing boat, the width of a bath, the weight of a full-grown person, and every ounce of it was a single armoured invertebrate that once walked on land. Its name is Arthropleura. When the description was published online in late 2021, in the Journal of the Geological Society, it was recognised as the largest arthropod fossil ever found in Britain, and among the largest land invertebrates ever known to science. Not a reptile, not an early mammal, a relative of the millipede, grown to a size that no millipede, no centipede, no insect, no crab has reached on land in all the time since. And it did not live in the age of dinosaurs, it lived long, long before them. So settle where you are, let the pillow take the weight of your head, and let your shoulders come down from wherever they have been holding themselves all day. There is nowhere you need to be tonight except here, walking slowly backward through deep time. You do not have to remember any of these names. You do not have to keep track of the dates. You can simply follow the sound of them and let the ancient world assemble itself in the dark behind your eyes. We are travellers together, and we have a long, quiet way to go. To reach the world where Arthropleura walked, you have to travel back through an amount of time that the human mind is not built to feel. The block on the beach at Howick came from rock laid down in the Carboniferous period. That period ran from roughly 359 million years ago to about 299 million years ago. 60 million years from start to finish. To give that a shape you can stand next to, consider this. The first dinosaurs would not appear for more than 100 million years after the Carboniferous ended. When Arthropleura was alive, there was no Tyrannosaurus, no Triceratops, no Brachiosaurus, not even their small and modest ancestors. There were no birds, there were no flowers. The great reptiles that people picture when they hear the word prehistoric were themselves unimaginably far in the future. Sit with that for a moment, because it changes the scale of everything that follows. We tend to file all of the deep past into one drawer marked long ago. But the distance between you and a dinosaur is smaller than the distance between that dinosaur and Arthropleura. This is an older world than the one the dinosaurs knew, a more alien one in many ways, and it belonged, above all, to the arthropods. That word covers a vast and ancient family. Insects belong to it. So do spiders and scorpions, crabs and shrimp, centipedes and millipedes. Bodies built in segments, wrapped in a hard external shell, carried on jointed legs. Today they are almost all small. The largest land arthropod now alive is a coconut crab, and it could sit comfortably in the space that one of Arthropleura's body segments once filled. But in the Carboniferous, the arthropods were not the background of the living world. In many places on the forest floor and along the water and in the air above it, they were the giants. This was their age. And to understand how they grew so large, you first have to breathe the air they breathed. Imagine the forest closing over you. The Carboniferous coal swamps spread in a broad green belt across the tropics of a world whose continents were still drifting toward one another. The air is warm and thick and wet, the kind of heavy, unmoving warmth you feel near the equator, where the temperature barely changes and the humidity never lifts. There is water everywhere underfoot. The ground is not soil in the way you know soil. It is peat, waterlogged and spongy, a deep mattress of fallen plants that never fully rotted away. It smells of standing water and slow decay, rich and green and faintly sour. Every step would press dark water up around your foot. Above you stand the trees, and they are like nothing in any forest today. These are lycopsids, giant relatives of the small club mosses that now creep low across the ground. Here they are colossal. Lepidodendron and Sigillaria rose in straight, branchless columns for much of their height, then split into a crown near the top. The tallest reached between 100 and 165 feet, which is 30 to 50 meters, the height of a 15-story building grown out of what is essentially a giant moss. Run your hand along the trunk of a lepidodendron, and you would feel it patterned all over in diamonds, a texture like woven scales, each diamond the scar where a long leaf once attached. Some people compare that bark to the skin of a reptile, though no reptile worth the name yet existed to compare it to. The canopy above these trunks is dense, and the light that reaches the swamp floor is green and dim and filtered, moving as the crowns move. Ferns and horsetails crowd the lower levels. Water channels wind between the tree bases. There are no bird calls, because there are no birds. There is no rustle of fur, because there are no mammals of any size. What moves here moves on many legs, or on wings that are not feathers, and the silences between are long, and the air itself is different. This is the heart of it. The Carboniferous atmosphere is thought to have carried far more oxygen than the air you are breathing now. Today, oxygen makes up about 21% of the air, roughly 1 part in 5. During the peak of the Carboniferous, and into the period that followed, that figure is estimated to have climbed toward 35%. More than 1 part in 3. It is the richest the atmosphere is believed to have ever been, before or since. You would not survive long in that air unchanged, but if you could, you might feel the difference in strange ways. Fires would be one of them. With that much oxygen, fire catches more easily and burns hotter, and it can spread through vegetation that would barely smoulder today. The Carboniferous forests burned often. We know this because the coal those forests became is threaded with fossil charcoal, a black and silky material called fusain, and it makes up an estimated 10 to 20% of Carboniferous coal by volume. That is a great deal of burning, preserved as crumbling black layers, ash from wildfires that swept the swamps under a sky heavy with oxygen. Somewhere in the middle distance, on many days, thin smoke would have been drifting up through the trees. Now the reason this thick, oxygen-rich air matters so much to our giants comes down to a single fact about how arthropods breathe. And here is where you have to unlearn something gently before we go on. You breathe with lungs. You pull air into 2 great sacs in your chest, and blood picks the oxygen up there and carries it, pumped by your heart, to every tissue in your body. An arthropod does none of that. It has no lungs of the kind you have, and for the most part no blood-borne oxygen delivery at all. Instead, insects and their kin breathe through a system of tiny tubes. These tubes are called tracheae. They open at the surface of the body through small holes, and they branch inward, dividing again and again into ever finer channels, until the very smallest of them reach individual clusters of cells deep inside. Oxygen does not get pumped along these tubes. It seeps. It moves by simple diffusion, drifting from where there is more of it, out in the air to where there is less, deep in the working tissue. No heartbeat drives it, no lungs draw it in. The whole delicate arrangement runs on the quiet physics of a gas spreading from crowded space to empty space. For a small animal, that works beautifully. The distances inside a housefly are tiny, and oxygen diffuses across them with ease. But diffusion has a problem, and the problem grows with size. The bigger the body, the farther the oxygen has to travel down those branching tubes to reach the core, and the harder it becomes to supply the deepest tissues fast enough. There is, in this picture, a natural ceiling on how large an air-breathing arthropod can grow. Push past it, and the animal in the middle begins, in effect, to suffocate. So here is the elegant idea that has been told about this world for a long time. If the limit on arthropod size is set by how well oxygen can diffuse inward, then raising the oxygen in the air should lift that limit. Richer air means oxygen crowds into those tubes at higher pressure and pushes deeper into the body before it runs thin. The ceiling rises, and under a sky near 35% oxygen, arthropods could grow to sizes the world had never seen. On that reading, Arthropleura and the giant winged insects and the great scorpions are all children of that thick carboniferous air, made possible by an atmosphere that would eventually thin back down and take their gigantism with it. It is a clean and satisfying explanation, and you will hear it told with great confidence. But you should know, calmly and clearly, that it is now contested. The simple link between high oxygen and giant bodies has been questioned by careful researchers, and the debate is genuinely open in current science. One recent study looked closely at the actual breathing tubes inside insect flight muscle, measuring the space those tubes take up across many different species and sizes, including estimates for the giant griffinflies themselves. If oxygen supply were the thing holding body size in check, you would expect the plumbing to change dramatically with size. The measurements did not show that. The tube space in the flight muscle did not scale strongly with how big the insect was. That is a real problem for the tidy oxygen story, and it is not the only one. Other scientists have offered other constraints entirely. Some point to the danger of too much oxygen for the young, arguing that soft-bodied larvae in a high-oxygen world might face something closer to poisoning than plenty. Others look to the geometry of surface and volume, the way a body's outside grows more slowly than its inside as it enlarges. We will come back to all of this later, when we have met the giants themselves and can weigh the idea against the animals it is meant to explain. For now, simply hold the whole picture loosely. High oxygen is real, the giants are real. Whether one straightforwardly caused the other is a question the science has genuinely reopened, and honesty is worth more than a neat ending. Because here is a detail that ought to make you pause. Not every giant arthropod waited for the Carboniferous oxygen peak. The largest arthropod of all, by some measures, lived tens of millions of years earlier, in an older world whose air was not nearly so rich, and it lived in fresh water rather than on land. We will reach that creature in time. Keep it as a small stone in your pocket, a reminder that the world rarely tells its stories as simply as we would like. One spike of oxygen is going to feel like too small a box to hold all of these animals, once you have seen how far apart in time and place they truly lived. Still, there is no question that something extraordinary was happening in these swamps. Whatever set the size of these bodies, the Carboniferous forests grew and fed a community of arthropods larger than anything the land has carried before or since. The peat beneath them, thick with undecayed plants, was storing so much carbon that it would eventually squeeze down into the coal seams that powered a much later age. The very name Carboniferous means coal-bearing. You are walking, in your mind, through the raw green beginning of the world's great coal. And that too has its quiet argument, worth a moment's honesty. For a long time people explained the sheer volume of Carboniferous coal with a simple tale. The trees, the story went, had evolved tough new tissues to stand tall, and the fungi that break such tissues down had not yet caught up, so the dead wood piled up unrotted for millions of years. It is a lovely idea, and you may have heard it. But a careful study in 2016 looked hard at what these coals were actually made of, and found that the story does not hold together as cleanly as it once seemed. The tough material was not the main thing forming the coal, and the decay of it was already underway. The better explanation, the researchers argued, has more to do with the particular climate and the particular arrangement of the continents in that age. wet lowlands sinking and flooding at just the right pace to bury plant matter faster than it could rot. The old fungal tale is still repeated often. Real understanding, here as everywhere, is slower and less tidy than the tale. Let all of that settle, the way silt settles in still water. You're standing in a warm green forest under a sky heavy with oxygen, more than 300 million years before the present, more than 100 million years before the first dinosaur draws breath. 15-story club mosses rise around you in diamond-scaled columns. The ground breathes water at every step. Somewhere out of sight the swamp is quietly burning, and somewhere else it is quietly turning into coal. There are no voices, no engines, no bells, nothing your own age would recognize. Only warmth and green light and the slow physics of a gas seeping into 10,000 small bodies through 10,000 narrow tubes. Take one slow, easy breath of your own, here in the present, and let it out without hurry. You have come a very long way already tonight, farther than the whole age of the dinosaurs, and there is no rush in any of it. Time is the one thing this world has an endless supply. We can afford to move as slowly as the water moves through the peat. Now let your attention come down out of the high green canopy, down past the branchless trunks, past the diamond-patterned bark, past the crowded ferns and the coiled young horsetails, down toward the wet, dark floor of the swamp, where the light is dimmest and the peat is deepest and the smell of slow decay is strongest. This is where the biggest of them lived, not in the treetops and not in the open sky, but here, close to the rotting ground, moving among the fallen leaves and shed bark and the soft remains of last season's growth. This is the world that made the animal on the beach at Howick, the armoured giant whose broken plates we started with, before it was rock, when it was still alive and slow and enormous. The oxygen story may be contested, and the coal story may be tangled, and the dates may stretch the mind past where it wants to go. All of that can wait. What cannot wait, what has been patiently drawing closer this whole time while we talked of air and trees and deep time, is the first of our giants, down here on the floor of the swamp where the light barely reaches. Look straight up and the canopy closes over you like a green ceiling 100 feet away. The trees holding it are lycopsids, distant relatives of the small club mosses that today would fit in your palm. Here they stand 30 to 50 meters tall, roughly 100 to 165 feet. Lepidodendron is the one you will remember. Run your eyes down its trunk and the bark is patterned in tight diamonds. Each diamond is a scar, a cushion where a leaf once anchored to the wood. The surface reads under your fingers like reptile skin stretched over a standing column. The whole trunk is a tower of these leaf cushions, packed close, rising past you into shadow. Sigillaria grows here too, taller and more slender, its scars set in long vertical rows. Neither tree has bark and wood arranged the way a modern oak does. Most of that great height is soft tissue, a green skyscraper built more like a wet reed than a timber beam. Now feel the air. It is warm and close and heavy with water. You're standing near the equator, in a lowland swamp that never truly dries out. Every breath comes thick, almost drinkable. And there is something else folded into that breath, something your body would register within a minute of arriving: the oxygen. The Carboniferous atmosphere held far more of it than the air you know, close to 35% by the best estimates, against about 21% today. You cannot see it or smell it directly, but it is the invisible fact underneath everything alive in this forest. It is the reason the animals here grow to sizes that will never come again. That richer air also changes the rules for fire. With so much oxygen present, a flame catches faster and burns hotter than anything in the modern world. A lightning strike in the canopy does not smoulder and die, it runs. Fire crosses the dry-standing litter, and the resin-heavy debris and climbs the lower trunks, and the whole forest becomes flammable in a way ours is not. So the smell you carry with you is never only the sweet rot of the swamp. Threaded through it most days is smoke. Look toward the horizon between the trunks and you may see it, a grey smear drifting low over the water, ash sifting down through the humid air and settling onto the peat like a fine dark snow. That ash is not lost. It becomes part of the record. When Carboniferous fires burned through this vegetation, they left behind charcoal, and that charcoal was buried and pressed into the coal seams along with everything else. Geologists have a name for it: fusen. You would know it at once if you held a piece. It is black and silky, light in the hand, crumbling into soft flakes that mark your skin, and it is everywhere in these coals. Fusen makes up an estimated 10 to 20% of Carboniferous coal by volume. Stop and let that number settle. As much as a fifth of the buried forest, by some measures, is fossil charcoal. That is not the trace of one rare disaster. It is the signature of fire as a constant. A forest that burned and regrew and burned again across millions of years, its flames fed by an atmosphere unusually eager to carry them. Beneath your feet, the ground is doing its own slow work. This is not soil in the ordinary sense. It is peat, waterlogged and dense, made of plants that fell and sank and never fully rotted. Press down and it gives like a soaked sponge, dark water welling up around the edge of your foot. The smell rising from it is the smell of an entire forest decaying in place, rich and sour and organic, the odour of a compost heap the size of a continent. Very little oxygen reaches down into that saturated mass, so the bacteria that would normally finish the job stall out. The dead plants simply accumulate layer on layer, year on year, sinking under their own weight. That is the quiet miracle of this place. The swamp is building coal in real time, though it has no idea it is doing so. Every fallen trunk, every mat of leaves, every drift of settling ash is another thin page pressed into the growing pile. Bury peat deep enough for long enough, under enough heat and pressure, and it hardens. First into lignite, then into the black coal that will one day sit in seams far below a future landscape. The forest around you is not just alive. It is fuel in the making, a fossil energy field laying itself down one wet season at a time. Before we walk deeper into it, let me ask one small thing of you. If this slow journey through deep time is helping you towards sleep, follow or subscribe wherever you're listening, on Spotify, on YouTube, or in your podcast app of choice. Then let the forest close back in around you, because the same waterlogged burial that makes coal can, under the right conditions, make something far rarer. It can make a window. About 307 million years ago, not far from where you now stand in this imagined swamp, a river system laced the lowlands of what will one day be Illinois. When those rivers flooded, they dumped mud fast, smothering whatever lay on the bottom before it could rot or be scattered. That fast-dumped mud is now a rock called the Francis Creek Shale, and locked inside it is one of the finest records of Carboniferous life anywhere on Earth. Paleontologists call the site Mason Creek. What makes Mason Creek extraordinary is not just what died there, but how it was kept. A dead animal or plant settled into the soft mud and was buried quickly within hours or days. As its body began to break down, the chemistry around it shifted, and iron in the surrounding water reacted with carbon from the decaying tissue. Around each little corpse, a hard mineral shell began to grow. That mineral is cedarite, an iron carbonate, and it formed a rounded nodule of ironstone with the organism sealed at its heart. The body itself might vanish, but the stone had already taken its shape, an iron-bound cast of a thing that lived and died in the swamp. Picture holding one now, it is dull and grey-brown, smooth, heavier than you expect, the size of a potato or a clenched fist. There is nothing on the outside to tell you what is within, but strike it correctly or let frost and time do the work and the nodule splits along a natural seam straight through its middle. It opens like a locket, and there, pressed into both halves, is the fossil, rendered in 3 dimensions rather than crushed flat, a fern frond with every leaflet intact, the delicate wing of an insect, a soft-bodied creature that in almost any other rock would have rotted to nothing, here preserved because the stone grew around it before decay could win. The sheer variety is what stays with you. Mason Creek has yielded more than 465 animal species and over 350 plant species. That is not a graveyard of a few tough shells. It is a near census of an entire coal swamp world, hard bodies and soft bodies alike, plants and animals that lived along the same waterlogged ground you're standing on. Because siderate is willing to encase the fragile as readily as the durable, Mason Creek captures the parts of an ecosystem that the fossil record almost always throws away. It is as close as you will ever come to walking through the doorway of this forest and finding it for a moment still furnished. Hold those 2 fates side by side. Most of this forest becomes coal, its individual lives blurred and pressed into a black seam that keeps the fact of the forest, but erases its faces. A lucky few, buried fast by a flooding river and sealed in iron, keep their faces instead. A single fern, a single wing, a whole small body, softness and all waiting inside a grey stone for the seam to open. The swamp keeps its record in 2 different hands at once, one broad and anonymous, one intimate and exact. For now, though, you're still here inside it. Before any of that burial is done, the heat sits on your skin. The air stays thick and oxygen-heavy in your chest, and the smoke on the horizon is thinning now, the last of the ash drifting down onto the black water. Around you the great lycopsid trunks rise into their green ceiling, diamond-scaled and silent, and the light that reaches you is dim and filtered and steady. Underfoot the peat holds your weight and slowly gives, releasing its dark, decaying breath. The leaf litter is deep in this stretch, layered and rotting, a soft brown mat spread across the waterlogged ground. On that warm, waterlogged floor, something long and armoured is already moving through the leaf litter, and it is time you met it. On that warm, waterlogged floor, something long and armoured is already moving through the leaf litter, and it is time you met it. On that warm, waterlogged floor, something long and armoured is already moving through the leaf litter, and now it is beside you. You do not see it all at once. You see a ripple first, a slow wave passing under the fallen fronds, the way a current moves beneath still water. Then the front of it clears the debris, a blunt rounded head, low to the ground. Behind that head a body that keeps coming and coming, plate after plate, longer than you first believed anything on land could be. Stand still and let it pass. It is not hunting you. It is not hunting anything. This is Arthropleura, and it is simply grazing its way across the forest floor, exactly as it has done for its whole quiet life. Look at the shape of it while it moves. The body is built from many segments, each one capped by a curved armoured plate called a tergite. The plates overlap front to back, stacked like roof tiles laid down a long slope, so that the whole animal flexes as it walks. Along both sides run the legs, dozens upon dozens of them, short and paired, rising and falling in slow-travelling waves. It is a millipede in body plan, a relative of the small coiled things you might find under a log today. But this one has been scaled up past all modern comparison. Let the number settle over you gently. The best measured specimen of Arthropleura is estimated at about 8.6 feet long. That is taller than a doorway laid on its side, longer than most couches, a single animal you could not step over without effort. It measured close to 1.8 feet across the widest plates, wider than your 2 hands held fingertip to fingertip, and it weighed, by the current estimate, somewhere near 110 pounds. That is the mass of a grown human, carried low on many little legs, gliding through the ferns without hurry. Hold that in your mind as it passes. The largest land invertebrate ever known to have lived. Not the largest of its time only. The largest ever. Before it and after it, Nothing without a backbone has grown this big on dry ground. You are standing beside a record that has held for more than 300 million years. Nothing else in this forest reaches its scale. The trees do, the great-scaled lycopsids overhead, but they are rooted and silent. This is the largest thing that moves here, and it moves like something in no danger at all. There is a calmness to real size. Nothing on this floor can threaten a body this long and this armoured, so it never rushes. It grazes. It flows. It takes the morning to cross a clearing you could cross in 10 steps. Now let me tell you how you came to know it, because the knowing was slow, and it happened far from this warm green world on a cold grey beach. The place is Howick Bay, on the coast of Northumberland in the north of England. It is a storm-exposed shoreline, cliffs of hard sandstone standing over a beach of the same broken stone. In January a block fell. A slab about the size of a heavy door came loose from the cliff face and dropped onto the sand below, and when it landed it split, and its fresh inner face caught the light. Across that face ran a row of curved, overlapping segments, ridged, tile-like, far larger than any arthropod fossil ever recorded in Britain. That fallen block held a piece of Arthropleura. Not the whole animal, but enough. Enough articulated exoskeleton, still joined plate to measure and to scale. The scientific description was published in the Journal of the Geological Society at the end of 2021, and the verdict was clear. Roughly 8.6 feet long, around 1.8 feet wide, near 110 pounds in life, the largest arthropod fossil ever found in Britain, and a body plan among the larger terrestrial invertebrates known to science. This particular animal lived about 326 million years ago, deep in the Carboniferous, more than 100 million years before the first dinosaur drew breath. And here the sediment told a second story, one that quietly revised what people had long assumed. For years the picture had Arthropleura wading through the deepest, wettest coal swamp, the classic peat bog of the age. But the rock it was buried in at Howick Bay suggested something drier and more open. Open woodland near the coast, a river channel cutting through it, sand shifting and settling, not the black waterlogged muck of the swamp interior. So the animal beside you now may have preferred exactly this kind of ground. Firm enough to walk, wooded but not drowned, lit in places by gaps in the canopy where the sun came down in warm bars. Feel that adjustment for a moment. It is a small thing and a large thing at once. The giant of the coal forests may not have been a creature of the deepest swamp at all, but of its dry margins, its open groves, its riverbanks. The evidence is written in grains of sand, and the grains say woodland. Watch it feed while I go on. The head dips. The mouth parts work at the litter, at the soft rotting stems and fallen leaves and the pulp of things that have already died and begun to break down. It is turning decay into more of itself, slowly, all day. And for the longest time, no one could say for certain that this was what it did. Because for roughly 150 years, through all the study of this animal, one crucial piece had never been found. No one had ever seen its head. Think about that. Scientists knew the body from many fragments across many sites. They knew the plates, the legs, the sheer length. But the head, the part that would finally reveal how it ate and how it sensed the world, stayed missing. An animal known for a century and a half and still faceless. So the oldest question hung open. Was this giant a peaceful grazer, or was it a hunter, an armoured predator sweeping the forest floor for prey? The answer came in 2024. A head fossil of Arthropleura was described at last by L'Heritier and colleagues in the journal Science Advances. The first head ever recovered for this animal, after all those decades of headless bodies. And when researchers finally looked at that face, the picture assembled itself with unusual clarity. Let me describe what they saw, because it is the face of the creature moving past you now. Two eyes, set out on short stalks, club-shaped at their ends, lifted a little away from the head so the animal could take in the ground around it. A pair of slender antennae, feeling ahead through the litter, reading texture and scent from the debris. And a set of mouth parts underneath, mandibles, and behind them 2 pairs of maxillae, small jointed tools for handling and processing food. Nothing about that mouth is built for seizing struggling prey. There are no fangs, no venom, no grasping, hooked limbs to pin another animal down. Put those clues together the way the scientist did. Short legs, a slow, deliberate gait, a body too heavy and too unhurried to chase anything. Mouthparts made for working over soft, yielding material rather than tearing flesh. Every line of evidence points the same direction. Arthropleura was, in all likelihood, a slow-moving detritivore, a processor of the dead and the fallen. It cropped rotting vegetation, decaying wood, the endless soft carpet of the forest breaking itself down. It was, for all its terrifying scale, one of the gentlest large animals you could imagine. Now I want to be honest with you about what we do and do not know, because honesty is part of the calm here. That conclusion, detritivore rather than predator, is an inference. It is drawn from the anatomy of the head and the manner of the animal's movement. It is not drawn from preserved gut contents. No one has yet found an Arthropleura with its last meal still inside it, fossilized in place, to settle the matter beyond all doubt. The detritivore reading is the best supported answer we have, and it fits the evidence well, but it remains a reasoned interpretation rather than a direct observation. Its mouthparts even share a few features with the mouthparts of carnivorous relatives among the centipedes, which is a reminder that living bodies rarely sort themselves into tidy boxes. So hold both things at once. The animal beside you is almost certainly harmless, a grazer of rot, no threat to you or to anything that can move, and there is a small, honest margin of the unknown around it, the space where the fossil record simply has not spoken yet. That margin does not make it dangerous, it only makes it real. Real things keep some of their secrets. Let the great body finish passing. The last few segments clear the ferns, the final pairs of legs lift and fall, and the tail end slides away into the green. It leaves something behind, though, pressed into the soft ground. A trail. If this is your first time walking with the Dinosaur Hour through the deep past, settle in and let the forest close around you. There is no need to follow the dates or hold the numbers. Let them drift over you like the warm swamp air. I will carry the thread. You only have to rest and breathe and let the ancient world unfold at the pace of something very large and very slow. That trail it left is worth kneeling beside, because trails are their own kind of fossil, and Arthropleura left some of the most extraordinary in the world. When an animal this size walks across soft mud, its many legs press in 2 long parallel rows of small blunt prints, and if the ground is right and the burial is gentle, those rows can survive as stone. Paleontologists have a name for this particular pattern of tracks. They call it Diplycnites cuithensis. 2 neat rows of closely spaced footfalls running side by side across ancient floodplain sediment, made by a many-legged giant walking through. The most famous of these trackways are found at the Joggins Fossil Cliffs, on the coast of Nova Scotia in Canada, and at El Cobre Canyon in New Mexico. And their scale tells you the scale of the walker without a single body plate present. Some of these trackways run up to about 20 inches wide. Kneel and imagine that. The full breadth of the animal that made it, legs to legs, wider than a car tyre, pressed into mud that later turned to rock. You do not need the creature itself. Its walk alone is enough to fill you with the size of it. There is a quiet lesson in these tracks, and I will give it to you plainly, because it is another honest edge of the science. Some of the early trackways found at Joggins were, at first, attributed to Arthropleura, and some of those were later reassigned to a distinct ichnospecies, a separate named category of trace. The record of footprints, like the record of bodies, gets revised as we look more carefully. Names shift, attributions move. The past does not arrive finished, it arrives in pieces, and each generation fits a few more of them into place, and sometimes takes an old piece back out again. That is the truth beneath all of this. What you're being told about Arthropleura tonight is not ancient certainty. It is recent knowledge, some of it only a couple of years old, still warm from discovery. The head that finally answered the predator question is newer than many of the phones in the world. The trackways are being sorted and resorted even now. Before we lift our eyes from this floor, let me say one plain thing to you, wherever you happen to be listening tonight. If these slow walks through deep time are the kind of thing that carries you down into sleep, follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. That way the forest is always here when you need it. And now, back to the warm green dark and the last of the giant that just passed. Stay low with me a moment longer, down here at the level of the litter, and take in the world Arthropleura lived inside. The air is warm and thick and wet, the way air feels just before rain that never quite comes. It sits heavy in your lungs, richer in oxygen than any air you have ever breathed, and it makes even stillness feel dense. Above you the trunks rise, the great lycopsid trees, their bark patterned in diamonds like the skin of some enormous reptile, though no reptile that large yet exists. Those trees climb 30 to 50 feet and far higher, up into a canopy you cannot see through from here. The ground itself is alive with slow decay. Heat, waterlogged and dark, breathing out the smell of things breaking down, the same soft mass that will one day be pressed into coal seams beneath future continents. Everywhere around you the forest is dropping pieces of itself, fronds and stems and bark, and everywhere the litter is thick and rotting and rich. This is a banquet for a detritivore. An 8.6-foot animal that eats decay could hardly ask for a better home than a forest forever falling apart and feeding on its own ruin. And it was a still world for a creature like this. Slow, patient. There were no fast large hunters on this floor to send it fleeing, because it had no need to flee. Nothing could get through that armour, and nothing could move a body that size with any urgency anyway. So it simply grazed, hour upon hour, through litter and rot and the soft wreck of the canopy, an armoured giant with a gentle mouth, turning the dead forest back into life. Take one slow breath of that heavy air with it. Feel how thick it is, how green, how warm against the back of your throat. This is the high point of the invertebrate world, the moment when a body without bones grew as large as any body without bones ever would. You're standing inside the record, the single, longest, heaviest land animal ever to live without a spine is moving away from you through the ferns, and it will never be matched, not once, in all the ages that follow. There is a tenderness in that if you let yourself feel it. The largest of its whole kind, and it was harmless. It hurt nothing. It hunted nothing. It walked the drier margins of the coal forest and ate what was already gone, and left behind 2 long rows of footprints, and, in one lucky slab of English sandstone, a piece of its armoured back for us to find 326 million years later. That is the whole of its quiet life, as much as we can read it. A giant that asked for nothing but rot and warmth and time. Let your attention widen now, slowly, the way a held breath eases out. The forest floor has given you its giant, and its giant has passed. But the Carboniferous world does not end at the litter. It rises, it climbs the scaled trunks, up through the layered canopy, up toward gaps where the heavy air thins into light, and the trees give way to open ground. Because this forest is not endless woodland. It breaks, here and there, into clearings and channels and standing water. Rivers thread through it. Broad, shallow wetlands open between the groves, sheets of warm water under an open sky, edged with reeds and low green growth. And over that open water, where the closed canopy cannot crowd it, the air belongs to something else entirely. Not a walker, not a grazer of rot, a flyer. You have met the largest thing that ever crossed this ground on legs. Now the world is about to show you the largest thing that ever crossed a sky on wings, and it lives out there, over the water, beyond the last of the trees. So let the armoured giant go. Let it fold back into the green behind you, another slow ripple under the ferns. Gone. Let your knees rise from the soft ground. Let the heavy warm air lift you with them. Let the sizes settle now, one body at a time, the way specimens lie in a long museum drawer. Begin on the ground with the heaviest of them all. Arthropleura. Measured along its armoured back, this one ran about 8.6 feet, nose to tail. That is nearly the length of a small car, laid out flat across the leaf litter. Across the middle it spanned about 1.8 feet, wider than your two open hands set side by side with the fingers spread. Its weight is estimated near 110 pounds. Picture a large dog poured into a segmented shell and you are close to it. That particular giant came from Howick Bay, on the storm-battered coast of Northumberland in England. A block of sandstone dropped from the sea cliff onto the beach, and its broken face showed curved plates stacked like roof tiles. The find was made in January 2018. The formal description followed in December 2021 in the Journal of the Geological Society. It stands as the largest arthropod fossil ever recovered in Britain, and among the largest land invertebrates ever documented anywhere on Earth. It walked roughly 326 million years ago. For all that bulk, it was almost certainly gentle. A head fossil, the very first ever found for this animal, after more than a century of study, was described in 2024. It showed stalked eyes, slender antennae, and mouth parts suited to grinding rather than seizing. Short legs. A slow gait. No venom. No grasping claws. The evidence points to a detritivore, an eater of rotting vegetation, drifting over the forest floor like a living rake. Its trackways survive too, paired rows of blunt footprints pressed into old mud at Joggins in Nova Scotia and at El Cobre Canyon in New Mexico. Some runs close to 20 inches wide. You could have walked beside it in safety, matching its patient pace. Now lift the scale off the floor and hold it against the open sky. Meganeuropsis permiana. This is the largest insect known to have ever lived. Its wingspan is reconstructed at up to 28 inches tip to tip. Set your forearm against a ruler, and one wing alone, near 13 inches long, would match it. From its head to the end of its slender body it measured almost 17 inches. It came from red mudstone at Elmo in Kansas, and it flew about 285 million years ago, in the early Permian. The whole animal was rebuilt from a single incomplete wing, first noted in 1937, then detailed by the Harvard entomologist Frank Carpenter in 1939. There is a cousin worth naming beside it. Meganeuropsis americana, lifted from Oklahoma rock in 1940, is known from a forewing fragment about 11 inches long. That piece rests today in the Harvard Museum of Natural History, and its rebuilt wing is the largest insect wing fossil ever found. 2 fragile slivers of stone, and from them the biggest flying insect in the history of the planet. Older, and better known to the public, is Meganeura monyi. Its wingspan ran from about 25.5 inches to a little over 28. It hunted over the wetlands of what is now Commentry, in France, roughly 300 million years ago, in the late Carboniferous. The first fossils turned up in the coal measures there in 1880. 5 years later, in 1885, the French naturalist Charles Brongniart gave the genus its name, which means large-nerved, built from the dense mesh of veins he could see running through the fossil wings. Those specimens still sit in the National Museum of Natural History in Paris. Both of these were griffinflies, relatives of the dragonfly, though not true dragonflies themselves. Bring the scale back down to the shore now to another hunter that kept its feet on solid ground. Pulmonoscorpius kirktonensis, a scorpion, and one of the largest that ever lived. Its biggest known individual is estimated to have passed 28 inches in length. That is the reach of a house cat stretched out, tail included, but armoured, and carrying a sting. It came from East Kirkton, in West Lothian, Scotland, a strange old landscape of volcanic lakeshore and hot springs. The paleontologist Andrew Jeram described and named it in 1994. Inside the fossil, he found book lungs, the folded breathing organs that prove it drew open air rather than water. This was no stranded sea creature. It was fully, permanently a land animal, with large lateral eyes, and no sign of the burrowing habit of its modern kin. The body plan reads as an active surface hunter, moving over the shore in daylight, and then the strangest of the roll call because it is both the largest and the oldest, and it belongs to a different world entirely, Jaekelopterus rhenaniae. What survives of it is mostly a single claw, a fossilised chelicera 18 inches long on its own. Hold that in your mind. Not the animal, the claw. From that one piece, scaled against smaller, more complete relatives, researchers estimated a body around 8.2 feet, and longer still once the claws are counted. That makes it, by that reckoning, the largest arthropod ever to have evolved. It was pulled from freshwater rock of the Wilwerath deposit in the Rhineland of Germany, and it lived about 390 million years ago in the early Devonian. Simon Braddy and Marcus Poschmann described the claw in the journal Biology Letters in 2007. It is often called a sea scorpion, but the common name misleads. The evidence points to rivers and lakes cool and clear, not the open ocean, and notice where it sits in time. It swam roughly 60 million years before the high oxygen peak that most giant arthropod stories lean upon. Its great size came earlier, in a thinner air, which quietly complicates any single tidy explanation. Before these figures harden in your mind into certainties, let one honest caution rest gently among them. Several of these full-body giants are reconstructions, not complete skeletons pulled whole from the rock. Meganeuropsis is rebuilt from wing fragments. Jaekelopterus is scaled up from that one enormous claw. The fragments themselves are solid, real, measurable evidence, held in real drawers in real museums, but the total lengths and spans are careful extrapolations, and they carry the honest uncertainty of any reconstruction. The scientists who made them would tell you the same, plainly, without apology. So hold the drawer open a moment longer, and let the bodies lie there side by side. The armoured grazer near 8.6 feet and 110 pounds. The freshwater hunter scaled past 8 feet from a single claw. The scorpion beyond 28 inches breathing open air on a volcanic shore. And the winged giants spanning up to 28 inches across, the largest ever, to lift off the ground under their own power, each one anchored to a place and a date. Elmo in Kansas, Commentry in France, East Kirkton in Scotland, the Rhineland, Howick Bay in the north of England. Real coordinates, real rock, real years counted in the tens and hundreds of millions. These are not monsters conjured from imagination. They are measurements taken with rulers and calipers from stone. And of all of them, it is the winged ones that still stir something when you try to picture them moving. The heavy bodies grazed and hunted along the ground, slow and armoured and close to the mud. But the griffinflies belong to the air above the swamp, out where the trees thinned and the water opened flat and bright. Lift your eyes from the forest floor now, up past the scaled trunks toward a shape gliding out over the open water. Lift your eyes from the forest floor now, up past the scaled trunks toward a shape gliding out over the open water. Lift your eyes from the forest floor now, up past the scaled trunks toward a shape gliding out over the open water. It moves without hurry, a long dark line held flat against the warm air. Two wings reach out on either side, narrow and stiff, catching the light like panes of thin glass. This is a griffinfly, and its name is Meganeura monyi. Across this open Carboniferous marsh, nothing else in the sky comes anywhere near its size. Measure it against your own body for a moment. From one wingtip to the other, this animal spans somewhere between 25.5 and 28 inches. That is wider than the reach of a grown adult's 2 open hands and forearms laid end to end. It is roughly the length of your arm from shoulder to fingertip, and then some. Imagine that width of wing, holding steady in the air above a shallow marsh, tilting only slightly as it turns. It is an insect. It is also as wide as a hunting hawk. You are watching one of the largest flying insects the Earth has ever produced. Not a dragonfly, though your eye will keep insisting that it is. The long body, 2 pairs of clear-veined wings, the blunt head heavy with eyes, all of it reads as dragonfly to a modern mind. The resemblance is real, and it runs deep. But this creature belongs to an older branch of the family tree, and to see it clearly you have to hold the difference gently in mind. Meganeura monyi is a member of an extinct order called Meganeuroptera. Scientists sometimes call them griffinflies, a name coined to keep them separate from the true dragonflies that fly over ponds today. Griffinflies are close relatives of dragonflies and damselflies, cousins on the same great lineage of winged insects. They share the general body plan, the paired wings, the predatory habit. But they are not true dragonflies, and calling them that would blur a distinction the fossils are careful to preserve. Think of them as the larger, older kin, flying tens of millions of years before any true dragonfly took the same shape into the same skies. So set aside the pond and its small darting jewels. Put yourself instead on the edge of a wide Carboniferous wetland, roughly 300 million years ago. This is more than 100 million years before the first dinosaur draws breath. The air here is warm and thick and heavy with moisture, sitting close to the ground like the inside of a greenhouse. Behind you, the great coal forest rises, its trees standing well over 100 feet tall, some reaching toward 160. In front of you, the trees thin and fall away, opening into shallow water, reed-like growth, and slow black channels winding through peat. And over that open water, the griffinfly patrols. Watch how it holds its wings. Unlike a butterfly, which folds its wings up over its back, or a beetle, which tucks them beneath hard cases, this animal keeps its 2 pairs of wings spread out to the sides even at rest. In flight they stay stiff and flat, worked by powerful muscles packed into the middle segment of its body. The wing beat is not a soft flutter. It is a controlled driving stroke, the kind that lets a hunter hang almost motionless in the air and then surge forward in a straight, hard line. Everything about the shape says predator. Everything about the size says this predator answered to almost nothing. Consider what it would take to lift a wing that long. Each wing is a thin membrane stretched over a scaffold of veins, and the longer you make that membrane, the more it wants to bend and tear under its own motion. Nature solved this with an intricate lattice of supporting veins running the length and width of each wing, a dense network that braced the membrane and kept it rigid through the stroke. When you look at a Meganeura fossil, that network is the first thing that seizes your eye. The wings are printed into the rock as a fine mesh of lines, close and crowded and precise, like the leading in a tall window. That mesh gave the animal its name, and the name carries a small buried story of its own. We will come to the fossil bed soon. First, stay with the living creature a little longer, out over the marsh in the heavy morning air. Think about where this animal can and cannot fly. A wingspan approaching 2.5 feet is a magnificent thing in open air. It is a serious problem inside a forest. Picture yourself trying to carry a wide, flat board, wider than you are tall, through a dense stand of trees. Every trunk, every low branch, every tangle of growth becomes an obstacle. You would have to turn the board, tip it, slow down, thread it through gaps. A griffinfly with wings held permanently out to the sides cannot fold them away to slip between trunks. In the crowded interior of the coal forest, those wings would catch and snag on everything. This is why researchers place the largest griffinflies out here, over the open wetlands and marsh, rather than deep inside the forest. The reason is simple and physical. Wings this wide need room. They need clear air above open water, where a hunter can climb, bank and dive without a canopy pressing down from above or a lattice of branches closing in from the sides. The forest edge, the marsh, the reed beds, the shallow lakes. These are the places where such a body makes sense. So when you imagine Meganeura in flight, do not imagine it deep among the giant trees. Imagine it in the bright open lanes between them, over water, with sky above and marsh below. There it hunts. And here we have to be honest with you about the difference between what the fossils prove and what we reasonably suppose. The fossils prove the size, they prove the shape, the wings, the venation, the predatory build. They do not prove moment by moment how the animal flew or exactly what it did with each stroke. For that, scientists reach carefully toward the living relatives, the modern dragonflies and damselflies, and borrow their behaviour as a cautious guide. Watch a large modern dragonfly and you learn what that guide looks like. It can hover, holding one spot in the air with rapid wing beats. It can shoot forward in a burst, snatching a smaller insect out of the air with its legs folded into a basket. It can perch on a stem, wings spread, and wait, launching only when prey passes within reach. From these habits, researchers infer that the giant griffinflies most likely hunted in similar ways. Some hunting done on the wing out over the water, some done from a perch near open water, a patient wait followed by a short, decisive launch. Its prey would have been other insects, the smaller flying things of the Carboniferous wetlands. Hold that word, inference, in your mind, because it matters here. We are not watching Meganeura hunt. We are reading its body, comparing it to living kin, and drawing the most reasonable picture the evidence allows. The picture is a good one. It is not an eyewitness account. In a world this old, that distinction is the difference between honest science and comfortable invention, and this quiet channel would rather stay honest, even half asleep. There are things the fossils simply will not tell you, no matter how long you look. One of them is colour. When you picture this griffinfly over the marsh, you may want to give it a hue, a sheen, some flash of iridescence like the blue-green gloss on a dragonfly's body today. Resist that gently. The fossils of Meganeura do not preserve the original colour of the animal. The pigments are gone, lost in the long chemistry of turning flesh into stone. Any colour you have seen painted onto this creature is a guess, an artist's choice, not a fact carried up out of the rock. So let it stay uncoloured in your mind, a dark shape against a bright sky. Honest and unadorned. The same restraint applies to sound. You might expect a wing that wide to make some noise as it beats, a low thrum, a dry rattle, a hum you could feel in your chest. Perhaps it did. But no sound survives in a fossil, no recording, no impression of a wing beat's pitch, nothing that lets anyone say with confidence what this animal sounded like as it passed overhead. So the scene stays silent, or nearly so, filled only with the sounds you can fairly imagine for a warm wetland, moving water, wind through reed-like growth, the soft business of a world without a single voice raised in it. The griffinfly itself we will leave unheard, because that is all the evidence honestly permits. What the rock does preserve, it preserves beautifully. And to see how well, you have to travel to a coalfield in central France, to a place called Commentry, where the first fossils of this animal came to light. In 1880, in the late Carboniferous coal Measures of Commentry, slabs of dark shale began yielding the print of enormous wings. Coal shale splits along flat plains, and when one of these slabs opens cleanly, whatever was pressed inside can appear on the freshly parted face like an image lifted out of the dark. On these particular slabs lay the wings of something no one had a name for yet. Long veined and far too large for any insect then known to fly. 5 years later, in 1885, a French paleontologist named Charles Brongniart gave the animal its name. He studied those wings closely, and it was the veins that caught him. That dense, crowded network of supporting lines running through the membrane was so striking, so unlike anything expected at that scale, that he built the animal's name directly around it. Meganeura. The word means, in effect, large-nerved, a reference to those great networked veins. He looked at the wing, saw the mesh, and named the whole creature for it. When you hold that in mind, the name stops being a label and becomes a description. Every time you say Meganeura, you're pointing at the wing veins that a careful 19th century scientist saw and could not forget. Picture the moment plainly: a slab of Carboniferous shale, dark and cool. On its surface, the fine tracework of a wing far longer than a human hand, printed in stone. And a researcher bent over it, following the lines with his eye, close enough to see that the network was too remarkable to leave out of the name. That is the origin of the word that has travelled ever since, through textbook after textbook into your ears tonight. The valid specimens of Meganeura monyi are held today in the National Museum of Natural History in Paris. They are not many. Giant wings, printed into splitting shale, are fragile things, and complete individuals are rare. But what survives has been enough to place this animal firmly among the largest known flying insects of all time, with that wingspan running from about 25.5 inches to something over 28. Enough to let scientists compare it, wing by wing, to its griffinfly relatives across the ancient world. Enough to anchor a whole chapter of the history of life at the point where insects grew larger than they ever would again. Why they could grow so large is one of the oldest questions in this field, and it circles back to the air itself. During the Carboniferous, atmospheric oxygen is estimated to have climbed far above today's level. The air you breathe now is about 21% oxygen. The air over this marsh may have held close to 35%. That is a profound difference, and for a long time it seemed to offer a clean explanation for the giants. The reasoning ran like this: insects do not have lungs, and they do not carry oxygen through their blood the way you do. Instead, they breathe through a branching system of fine tubes called tracheae that thread inward from openings along the body and carry air directly to the tissues. Oxygen moves through those tubes largely by passive diffusion, drifting inward along its own gradient rather than being pumped. Such a system works well at small sizes. The worry has always been that at large sizes, the innermost tissues might struggle to get enough air, because the tubes can only carry so much so far by drift alone. Richer air, the argument went, would ease that limit, letting insect bodies grow larger than the modern atmosphere would allow. It is a tidy idea, and you have almost certainly heard some version of it. But this channel owes you the honest state of the science, not just the tidy version. In recent years, the oxygen explanation has come under direct challenge. A detailed study examined the fine oxygen-delivering structures inside insect flight muscle across dozens of species, including estimates worked out for the giant griffinflies, and found that the space given over to those air tubes does not scale strongly with body size the way the old theory would predict. If oxygen supply were the hard ceiling, you would expect the biggest insects to devote dramatically more of their muscle to air tubes. The measurements did not clearly show that. So the debate is genuinely open. Oxygen may still be part of the answer. It no longer looks like the whole of it, and no careful person tonight should tell you otherwise. Let that uncertainty sit comfortably, the way an old question can. It does not shrink the animal. Whatever the exact cause, the fact remains that something in this ancient world allowed an insect to fly on wings the width of a small hawk, and that something has not returned in 300 million years since. The griffinfly over the marsh is real, its wingspan is measured, its fossils lie in a museum in Paris. The reason for its size is still being argued in laboratories, and there is a quiet honesty in admitting that the world can hand us a fact this large and keep the explanation partly to itself. So return to the animal and let the arguing fall away behind you. Stand again at the edge of the open water, in the warm heavy air, and watch it work the marsh. It climbs a little, wings driving in that stiff controlled stroke. It levels off, holding a line above the shallows. Below it, the surface of the water is dark and still, broken here and there by growth pushing up through the peat. The griffinfly banks tilting those long wings and slides across the open lane between the distant trees. Somewhere ahead, a smaller insect crosses its path, and the big hunter shifts, adjusts, and closes the distance with the unhurried economy of something that has done this 10,000 times. You will notice, if you let yourself, how patient the scene is. There is no frenzy in it. A large predator in rich air does not need to thrash. It holds, it waits, it moves once and well. That measured quality is part of why the griffinfly is such a fitting companion for a quiet night. It is enormous and it is calm, a huge old wing turning slowly over still water, asking nothing of you but that you keep watching. And there is a deeper stillness underneath the scene, the stillness of how much time separates you from it. 300 million years is a number the mind cannot really hold. Try it as distance instead. If each year were a single inch, 300 million years would stretch far enough to circle the Earth many times over, an unbroken line of inches running past every coastline on the planet and back again. All of that lies between your bed tonight and the moment this griffinfly banked over the marsh, and yet the wing left its print, and the print became stone, and the stone was split, and here it is, close enough to describe in a calm voice in the dark. Look once more at the head of the animal, blunt and heavy, dominated by large eyes. Those eyes are built to catch motion in open air, the flick of a smaller insect against the bright sky. This is a creature tuned to the visual hunt, to the clear lane over water where prey shows itself against the light. It is one more reason the marsh, and not the shadowed forest interior, is where you should keep it. In the dim tangle among the giant trees, such eyes would have far less to work with. Out here, over the open shallows, they command the whole bright field. Feel the world it belongs to, one more time, before you leave the sky. The trees behind you are not the trees you know. Their trunks are patterned in diamond-shaped scars where old leaves once attached, a texture closer to reptile skin than to any bark in a modern wood. The ground beneath them is waterlogged, dense with rotting plant matter, the raw material that long ages will press into coal. The air is rich and damp and warm, and it moves slowly. And through it, on wings the width of your outstretched arm, the griffinfly holds its patient line above the water, uncoloured, unheard, exactly as much as the fossils allow and no more. Now let your attention drift downward, away from the sky and toward the water itself. Follow the marsh to where it deepens and gathers into a proper channel, and follow that channel as it runs. The griffinfly stays above, growing smaller behind you, a dark line dissolving into the bright air over the reeds. Below, the water slides on, dark and slow, carrying the reflected light in broken pieces. It gathers into a lake, and the lake has an edge, and that edge is made of soft, dark mud. The world down there is a different one from the open sky. It is lower, closer, shadowed by the growth along the bank. The air near the mud is even heavier, thick with the smell of wet earth and decay. This is not a place for wide wings and long, clear hunting lanes. It is a place for something built low to the ground, something that moves along the shore rather than over it, something with a very different way of taking its prey. And in a particular corner of this ancient world, that shore was volcanic. Warm mineral water seeped up near the lake's edge, and the ground held the mark of old eruptions, and the mud along that Scottish shore would one day preserve, in exquisite detail, hunters that walked it. You can learn a startling amount from a single wing. Not a whole body, not an animal coiled in the rock, just one wing, pressed flat and turned to stone, and someone patient enough to read it. That patience is where much of this begins, in a French coalfield in 1880. The place is Commentry, in central France, a district of mines cut down into late Carboniferous rock. In those coal seams, in slabs of dark shale, collectors kept lifting out faint imprints. Delicate things. Fans of fine lines fossilized into the stone, each one no thicker than a thread. To an untrained eye they might read as cracks in the coal, or the ghosts of pressed leaves. They were wings, enormous ones. For 5 years they waited for someone to explain them. That someone was Charles Brongniart, a French paleontologist who set the fossils under a hand lens and studied what the lines were doing. What he saw was a network, a dense mesh of veins, branching and rejoining across the wing membrane, far more crowded than the veins in any wing he knew. In 1885 he gave the animal its name, Meganeura, large-nerved. He built the creature's very name out of that one feature, the crowded venation under his lens, not from the eyes, not from the legs, not from anything you would call a face, from the plumbing of a wing. And the wing told him its size. Stretched tip to tip, the largest of these Meganeura measured close to 2.5 feet across, somewhere between 25 and 28 inches. Hold that against your own body for a moment. That span is about the length of a grown person's arm, from the point of the shoulder to the tip of the longest finger. Now imagine that reach in a single flying insect, hunting low over standing water 300 million years ago. Brongniart could not watch it fly. No one ever will. So he did the honest thing, and named what he could actually see. The animal we now call Meganeura monyi was a griffinfly, a relative of modern dragonflies and damselflies, though not a true dragonfly itself. Like them, it was a hunter of other insects, patrolling the Carboniferous wetlands on those broad, vein-laced wings. The valid specimens still rest in the National Museum of Natural History in Paris, thin, dark impressions in stone, quietly holding the record of a vanished sky. That is the pattern worth settling into tonight. Again and again, these giants come to us not as bodies but as fragments. A single wing here, a single wing there. And around each fragment someone builds a whole animal, carefully admitting what they do not know. Follow the pattern west and forward in time to a low outcrop of red mudstone near the town of Elmo in Kansas. The rock here is early Permian, a little younger than the French coal, roughly 285 million years old. In 1937, from that red Permian mud, researchers lifted a single wing fragment, just one, incomplete, broken across, only a little over a foot long as it lay in the stone. A fragile brown ribbon of fossil, easy to overlook. It would turn out to be a piece of the largest insect that ever lived. The person who made sense of it was Frank Carpenter, an entomologist at Harvard, who spent a career reading fossil insects the way others read manuscripts. He had that one incomplete wing. From it, working through the geometry of the veins and the proportions of related griffinflies, he reconstructed the missing parts. He extended the broken edges. He estimated the full wing at around 13 inches long. He scaled the whole creature outward from there. The animal that emerged from his arithmetic is called Meganeuropsis permiana, and he laid it out formally in 1939. Its wingspan, tip to tip, reached close to 28 inches. Its body, head to tail, ran nearly 17 inches longer than your forearm. Picture it perched at the edge of an open marsh, wings held out to the warm air, a hunter the size of a hawk with none of a bird's bones inside it. It remains, by the measure of that wing, the largest insect known ever to have flown. Here is where the calm honesty of the work matters, and it is worth being clear with you before you drift off. That 28-inch wingspan is not a number lifted off a complete animal. No one has ever found a whole Meganeuropsis permiana. There is the wing, and there is a careful reconstruction extended out from it. The fragment is solid, real, measurable evidence. The full-bodied giant is a disciplined inference built on top of that fragment. Good paleontology holds both of those truths at once. It says, here is what the stone actually preserved, and here, separately, is what we think it means. It does not let the second quietly replace the first. This is a good place to pause and stay a moment inside that idea, because it is easy to forget once the size of these creatures takes hold of the imagination. Every measurement you hear tonight sits somewhere on a line between two things, At one end, the physical fossil, the thing you could hold. At the other, the animal reconstructed around it. A wing you can lay a ruler against. A wingspan you have to reason your way toward. The distance between them is exactly where the patient detective work lives, and the detectives kept working. 3 years after Carpenter's description, in 1940, another griffinfly wing surfaced, this time from Oklahoma. It was given its own name, Meganeuropsis americana, a close relative of the Kansas giant. What came out of the ground was a forewing fragment about 11 inches long, roughly 280 millimeters of fossilized membrane, reconstructed to its full length. That single wing stretches to around a foot, and it stands as the largest actual insect wing fossil ever recovered from the rock, not a reconstruction of a wingspan, the wing itself. Today, most specialists suspect that this Americana is not truly a separate animal at all. The best current reading is that it is a junior synonym of Meganeuropsis permiana, the same kind of creature under a second name, the way an object photographed from 2 angles can be mistaken for 2 objects. That fragment now rests at the Harvard Museum of Natural History in a collection drawer, an 11-inch piece of a wing that carried a body the size of a small hawk over Permian water. Sit with how thin the physical evidence really is. For the 2 largest flying insects ever described, the entire case rests on a handful of wings, 1 incomplete wing from Kansas, 1 forewing from Oklahoma, a scatter of vein-lined slabs from a French coal mine. From that, an entire order of aerial giants has been reconstructed, named, measured, and set back into their vanished skies. Whole animals, rebuilt from a wing or 2 by people willing to work slowly and say plainly where the stone ends and the reasoning begins. There is something restful in that restraint. These scientists were not guessing wildly. They were not inventing. They took the smallest honest scrap the earth gave them, a fan of fossil veins, and they asked it only the questions it could answer. How long was this wing? How are its veins arranged? How does that compare to living relatives whose whole bodies we do know? And when the wing could not answer, they let the question stand open, unfinished, rather than filling the silence with a comfortable story. So when you hear that griffinflies had wings as wide as a person's arm is long, hold the picture and the caution together. The picture is real enough. The wings existed. Brongniart saw their veins. Carpenter measured their length. But the flying giant hovering in your mind is stitched together from fragments by careful hands, and those hands were the first to tell you so. We cannot know their colours. Fossilization did not keep them. No honest reconstruction paints them in. We cannot know the sounds they made over the water. If they made any, we would recognize. What we have is the shape of a wing, the crowding of its veins and the quiet confidence of measurements that admit their own edges. It is enough. It is, in its way, more trustworthy than certainty would be. And these giants did not haunt the deep forest interior. Their wings were too wide to thread between the crowded trunks of the coal swamp. The reconstructions point instead toward open country, toward marshland and wetland and the bright margins of standing water, where a broad-winged hunter had room to turn and climb and drop onto smaller prey. Picture the largest of them there, out over the shallows, wings flashing in the humid light, then folding as it settles onto a reed at the water's edge. That is the world these fragments open onto. Not a museum drawer, but a wetland under a heavy oxygen-rich sky, warm and green and loud with smaller life. The wing in the stone is only a doorway. Walk through it, and you are standing on the shore of a Carboniferous marsh, watching giants that were rebuilt for you out of almost nothing. Stay with that water a little longer. The griffinflies owned the air above it, but they were not the only giants these shorelines carried. The same shallow, sunlit water that fed the flying hunters also lapped against low ground where other outsized creatures moved, closer to the mud, slower, and armed in a very different way. That water is worth staying with a moment longer. Follow that same water down to its muddy edge, where a low, tail-raised hunter is waiting in the volcanic Scottish light. Follow that same water down to its muddy edge, where a low, tail-raised hunter is waiting in the volcanic Scottish light. Follow that water down to its muddy edge. The light here is strange, thickened by a haze of volcanic steam drifting off the lake, and there, low against the ground, a hunter waits with its tail half raised. It is a scorpion, but not a scorpion like any you have ever turned a stone to find. This one is nearly 28 inches long, from the tips of its pincers to the curl of its sting. That is more than 2 feet of segmented armoured predator, resting on the warm mud of a shore that will one day sit in West Lothian, Scotland. Take a moment and hold that measurement against your own body. Nearly 28 inches is the length of your forearm and hand doubled over. It is longer than a house cat stretched nose to tail. Lay it across your lap and it would spill past both knees. This is Pulmonoscorpius kirktonensis, and the largest individual yet found is one of the biggest scorpions ever known to have lived. You're standing in the Carboniferous, in an interval geologists call the Visaean. The first dinosaur will not walk the earth for well over 100 million years. The air itself is different, richer in oxygen than the air you breathe now, and everything built from that air seems to have grown a little beyond the sizes you expect. The scorpion on the mud is one of those things. It does not know it is enormous. To itself, it is simply the right size for the world it lives in. Watch how it holds itself. The body is flattened and low, close to the ground, the way a scorpion's body always is. The 2 forward claws, the pincers, are held slightly open and forward, testing the air and the ground ahead. Behind the broad plate of the head, the segmented back tapers into a long muscular tail. At the tail's end sits the bulb of the venom gland and the curved point of the sting. Everything about the shape is familiar, and everything about the scale is wrong. The place that will hold its body for 330 million years is a strange one. This is East Kirkton, a volcanic lakeshore, and the ground you're imagining underfoot is not simple swamp mud. Hot springs feed mineral-rich water into the shallows. Volcanic activity simmers nearby, laying down ash and tuff, and dissolving minerals seep through the sediment. That combination is unusual, and it is also lucky. Water heavy with dissolved minerals is water that preserves. When a dead thing settles into that lake bed, the fine sediment and the mineral load can wrap around it fast enough to save details that almost never survive. That is why you can meet this scorpion at all. East Kirkton is a rare Carboniferous window, a place that kept not just the hard shells and the tree trunks, but the finer structures inside them. Around the scorpion's remains, the same beds hold plants and other animals from this early Carboniferous world. It is a snapshot of a lakeside community, sealed by heat and mineral and quiet burial. The volcano that made the shore so dangerous in life is part of what made it so generous in death. Come closer to the animal itself. Look first at the eyes. Most scorpions you might find today carry small eyes and hunt by touch and vibration, feeling the world through fine hairs rather than watching it. Pulmonoscorpius is different. It has large lateral eyes set to take in a wide field of the shore. Those big eyes are one of several ancestral features it keeps, features that later scorpions lost as their lineage changed. This is an older kind of scorpion, closer to the root, still wearing traits that vanished from the ones that came after. Large eyes tell you something about how it lived. An animal that invests in sight is an animal that uses light. Combine that with another absence. Search the fossil for the signs of a burrower, and you do not find them. There are no obvious adaptations for digging, no specialized limbs built to haul soil, none of the shovel-shaped modifications a burrowing arthropod tends to carry. This was not a creature that spent its days sealed underground, waiting for dark. Put those 2 clues together, and a picture forms. Big eyes and no burrowing gear point to an active predator that moved across the open surface of the shore, quite possibly by day. A diurnal hunter, out under the strange bright haze, watching the ground ahead of it with those wide eyes. Not an ambusher buried in a tunnel, but a walker, a searcher, patrolling the margin between water and land where small living things gather. You can imagine it stepping slowly across the warm mud, pincers forward, the whole long body following. Stay with that image, because it is doing careful work. Nothing here says the animal roared across the shore or ran anything down in a burst. It says the opposite of hidden. It says surface, and daylight, and eyes that mattered. Everything you are picturing is drawn from the body plan the fossil preserves, from anatomy read against the anatomy of scorpions we can still watch. It is inference, honest inference, and it is worth holding lightly even as you enjoy it. Now for the feature that gives this animal its name, and the one that matters most. Inside the fossil, preserved by that mineral-rich burial, researchers could identify book lungs. Say the name slowly, and you can almost see the structure. A book lung is a breathing organ built from thin folded sheets, stacked like the pages of a book, with air spaces between them. Blood flows along one side of each page, air fills the gap on the other, and oxygen passes across the thin membrane between. Modern scorpions breathe this way. So do spiders. It is the mark of an air-breathing land animal. Finding book lungs inside a fossil this old is a quiet kind of proof. It means Pulmonoscorpius was not tied to the water. It was fully terrestrial, fully committed to breathing open air, standing on land the way a scorpion stands on land today. And that matters because scorpions did not begin on land. Their deep ancestry runs back into the water, to aquatic forms that breathed through gills and lived submerged. Somewhere along that long line, the lineage crossed onto the shore for good, and traded gills for lungs that could pull oxygen straight from the atmosphere. The scorpion waiting on the East Kirkton mud is on the far side of that crossing. The book lungs in its body are the physical receipt. Here in stone is direct anatomical evidence that this giant was an air breather, terrestrial through and through, no longer bound to the lake it hunts beside. It can walk the shore, cross the drier ground behind it, and never need to return to the water to breathe. The water is a hunting ground now, not a home. That single fact reframes everything you are watching. This is not a sea creature that crawled out for a moment. It is a land animal, one of the large predators of its shore, breathing the same oxygen-rich air that lets so many arthropods of this age grow strange and large. The name itself carries the discovery. Pulmonoscorpius means, near enough, the lung scorpion. It was named in 1994 by the paleontologist Andrew J. Jeram, who studied these East Kirkton fossils and read the breathing structures inside them. The name is a small monument to the thing the fossil proved. Let that settle for a moment. A giant scorpion, longer than your forearm and hand together, walking a volcanic lakeshore in the deep Carboniferous, breathing air through folded pages of tissue, watching the ground with wide eyes under a steaming sky. It is a scene, and it is also a set of measurements and structures, each one read from stone. The wonder and the evidence sit in the same place. Here you should slow down and be honest with yourself about what you actually know. It is easy, standing on this imagined shore, to fill the scorpion's day with detail, to decide what it ate, how many of its kind shared the lake, how it moved, whether it hunted at dawn or noon. But most of that is not written in the rock. What the fossil truly gives you is a body, size, large lateral eyes, an absence of burrowing gear, book lungs. Those are the hard facts. Almost everything else is inference laid gently on top. Think about diet. It is reasonable to picture a predator this size feeding on the smaller animals of the shore, on other arthropods, on whatever it could catch and hold in those pincers and subdue with that sting. Reasonable, and probably close to true. But there is no preserved last meal here, no gut content that names a specific prey. The idea of what it ate comes from comparing it to scorpions and other predatory arthropods we can study, not from watching this one hunt. The prey list is drawn by analogy, and analogy is a good tool, but it is not the same as a witness. The same caution applies to how many there were. You might imagine the shore dotted with these scorpions, a whole population working the lake margin. Or you might imagine a scattered few, rare giants in a wide landscape. The fossils cannot easily tell you which. Population size does not preserve the way a claw preserves. Numbers like that are among the things the rock keeps to itself, and behaviour beyond the broad stroke stays uncertain too. That it was active, that it worked the surface, that it likely used the daylight. Those follow fairly directly from eyes and body and the lack of digging limbs. But the finer texture of its life, how it courted, how it raised young if it did, how it defended its ground, how long it lived, none of that survives here. To claim those details would be to invent them. The calm truth is better. You know a body plan, and from a body plan you can reason outward, carefully, and then you stop where the evidence stops. This is worth sitting with, because it is the honest shape of paleontology. You're not being handed a film documentary of a scorpion's day. You are being handed a body in stone and a set of trained inferences about what that body could do. The large eyes and the missing burrow gear give you an active, likely daytime surface hunting predator. The book lungs give you a true land animal. Beyond that, the shore grows quiet, and the responsible thing is to let it stay quiet rather than crowd it with guesses dressed as facts. So hold the two things together as you watch it one more time. There is the vivid animal, nearly 28 inches of armoured hunter, on a steaming volcanic shore. Wide eyes reading the mud, tail curled and ready. And there is the careful scientist version, a fossil from East Kirkton, named by Jeram in 1994, preserving book lungs and large lateral eyes in an early Carboniferous body, from which an active terrestrial predator is reasonably inferred. Neither version cancels the other. The scene is how you feel it. The fossil is how you know it. Why did it grow so large? You're standing in a world with more oxygen in the air than your own, an atmosphere estimated to have climbed toward 35% oxygen against the roughly 21% you breathe. Arthropods do not breathe the way you do. They have no single pair of lungs pumping air deep into a bloodstream. Even the book lungs of this scorpion work by letting oxygen pass across thin membranes, by diffusion rather than by force. For a long time, scientists have linked that quiet, passive style of breathing to a ceiling on body size, and linked the high oxygen of this age to the lifting of that ceiling. More oxygen in the air, the idea runs, meant oxygen could reach deeper into a large arthropod body, and so large arthropod bodies became possible. It is a clean and appealing idea, and you should know that it is not the whole settled truth. In recent years, the oxygen explanation has been questioned by careful new work, and the debate over what really let these animals grow so big is genuinely open. Oxygen may have been part of it. It may have set a permission, a door held open, without being the single cause. The giant on this shore is real, and its size is real, but the reason for that size is still being argued in the present, and the calm answer is to say so plainly rather than pretend the case is closed. What is not in doubt is that you are looking at one of the largest scorpions the world has ever produced, alive in a warm, wet, oxygen-rich age, on a shore made and preserved by fire and mineral water. It hunts the margin, it breathes the air, it watches the ground, and it belongs entirely to a vanished world more than 100 million years older than the first footfall of any dinosaur. Let your eye travel out from the scorpion now, across the wider shore. The lake steams under its haze. Somewhere behind you, the coal forests of this age crowd the wetter ground. Tall, scale-barked trees rising far overhead, their trunks patterned like the skin of some reptile that has not yet evolved. The air is thick and humid and heavy with the smell of growth and decay. Volcanic warmth breathes up through the ground near the springs. It is a green, wet, simmering world, and the giant scorpion is one small armoured citizen of it, walking its stretch of mud with ancient patience. There is a particular stillness to watching a predator that is in no hurry. Nothing on this shore moves it to rush. Its whole design is unhurried, low and deliberate, the pincers testing, the wide eyes reading, the long tail trailing its ready sting. You could watch it for an hour and see it cross only a few feet of ground. That slowness is part of what makes it a good companion for a quiet mind. It is enormous, and it is calm, and it is utterly at home in a world you will never touch. Before you leave this shore, fix the essentials of it in your memory, the way you might learn the shape of a room in the dark. Pulmonoscorpius kirktonensis, East Kirkton in what will be West Lothian, Scotland. A volcanic lakeshore fed by hot springs, its mineral-laden water sealing the dead into stone. An early Carboniferous age, the Visian, far back in deep time. A scorpion nearly 28 inches long, among the largest ever known. Large lateral eyes and no burrowing gear, marking an active surface hunter that likely worked by day. Book lungs inside the fossil, proving it breathed open air, fully a creature of the land. Named in 1994 by Andrew J. Jeram. Hold those, and you hold the animal. And hold, too, the honesty that came with it. The prey it caught, the size of its kind on the shore, the private details of its days, those you do not truly know. They are reasoned from the shape of the body and the habits of its living relatives, not witnessed in the rock. That boundary between what is known and what is inferred is not a weakness of the story. It is the discipline that makes the known part trustworthy. You can stand on this shore and feel the scene, and still keep a clear line around the part of it that is genuine evidence. Now let the light on the lake begin to change in your mind, and let the shore start to loosen its hold. The giant scorpion stays where it is, patient on its mud, breathing its rich air, one of the largest of its kind to ever cross onto land. You have met it fully. You have seen how big it grew, where it lived, how it breathed, and how carefully we have to speak about the rest. That is enough for this stretch of the journey. But this scorpion, for all its size, is not the largest arthropod waiting in the record. It is not even the largest that walked or swam through these ancient waters. To find the true giant, you have to go further down than the Carboniferous, further back than these coal forest shores, into an older world with less oxygen in its air, where a very different kind of hunter grew to a length that dwarfs even this. So loosen your grip on East Kirkton now. Let the volcanic haze thin, let the steaming lake and its patient scorpion fade behind you, and let deep time carry you backward once more. Stay a little longer on this warm ground and watch the largest scorpion the world has yet built move through an ordinary afternoon. The place is East Kirkton, in what will one day be called West Lothian in Scotland. The time is deep in the Carboniferous. In the interval, geologists name the Visian, roughly 340 million years back. Around you lies the edge of a small lake, and this is no ordinary water. It is fed and warmed by volcanic activity, and along its margins the ground has grown its own strange crusts. Look down at those margins first. Mineral-laden water has seeped up here for a long time, and where it cools it leaves pale deposits behind. Hot spring crusts ring parts of the shore in low, brittle shelves. The air near them carries the faint tang of dissolved minerals and warm stone. The lake surface is still this afternoon, barely stirred, holding the light like a sheet of dull glass. Beyond the water stand the tangled green forms of early land plants, but here at the open margin the ground is bare, damp and quiet. And onto that open ground comes the animal you have travelled all this way to meet. It is a scorpion, and it is enormous. The largest individuals of its kind reached over 28 inches from the front of the body to the tip of the tail. That is more than 2 feet of segmented hunter, longer than your own forearm and hand laid end to end, and then longer still. Its name, given much later, is Pulmonoscorpius kirktonensis. For now it has no name. It has only the afternoon, the warm ground, and the slow business of being alive. Watch how it holds itself. The body is built in the ancient scorpion pattern, the broad forward section carrying the walking legs and the pincers, the long tail curving up and behind. It does not rush. Cool-blooded animals borrow their pace from the world around them, and the warmth of this volcanic shore is exactly the kind of heat that lets a large arthropod move at all. So the scorpion moves as the heat allows. A few steps across the open flat, then a pause, a settling of the legs against the damp ground. Then stillness again, long and complete. Notice its eyes. This is one of the details the fossil itself insists upon, and it is worth dwelling on. Pulmonoscorpius kept large lateral eyes, set toward the sides of the forward body, a feature its living descendants have largely lost. Those big eyes tell you something plain about how this animal lived. This was not a creature built to hide from the light. Modern scorpions of comparable size tend to be night hunters, tucked into burrows through the bright hours. This one carried the wide eyes of an animal that worked in daylight, out in the open, scanning the ground it crossed. So picture it here in the afternoon glare, not skulking, simply present, its many eyes taking in the flat shine of the shore. And here is the other thing the fossil insists upon. There is no burrow. This animal shows none of the anatomy that a digging, retreating scorpion would carry. It has nowhere beneath the ground to vanish into, and by every sign its body offers, no impulse to try. It is an animal of the surface, committed to the open margin, hunting across the flats rather than lying in ambush from a hole. So the shore is not a place it passes over on the way to shelter. The shore is where it belongs. This bare, warm ground between the plants and the still water is its entire working world, and it moves over that world in daylight, unhidden. Let the scene slow with it. The scorpion halts near a low shelf of mineral crust and simply waits. This is most of what a cool-blooded hunter does. It waits, and it holds, and it lets the warmth keep its slow machinery running. You are watching an animal that spends far more of its day still than moving, an animal whose patience is not a mood, but a physiology. There is no urgency written into this body. There is only the long readiness of a predator that can afford to be unhurried, out here where the ground is warm and the light is generous. Now come close to the thing that makes this whole scene possible, the quiet detail hidden inside that armoured body. Pulmonoscorpius breathed air. Inside its trunk it carried book lungs, stacked thin folds of tissue arranged like the pages of a book, over which oxygen from the open air could pass into the body. This is not a small point. The distant ancestors of scorpions lived in water and drew their oxygen from it. This animal had crossed fully onto land. Its book lungs are direct physical proof, preserved in the fossil, that it took the open atmosphere straight into itself, the way a land animal must. So listen, in a manner of speaking, to what those lungs are doing as the scorpion rests on the shore. There is nothing dramatic to hear, and you should not imagine any sound, for no sound of this creature was ever preserved. There is only the slow interior rhythm of an air-breathing body at rest in the warmth. Oxygen crossing thin folded tissue, the unhurried metabolism of a large hunter, idling through the bright part of the day. Everything about this animal points the same way, toward stillness, toward patience, toward a life lived in the open air on warm ground. Follow that stillness a moment more. The lake barely moves. The mineral crusts sit pale along the margin. The great scorpion holds its place, its wide eyes turned to the flat, its book lungs working their slow exchange, its long tail curved and quiet behind it. Somewhere out across this shore there will be other small animals moving, the kind of creatures a surface hunter of this size could take. But be careful here and stay honest with the animal. The fossil does not tell you exactly what it ate. Its prey is inferred only from the general shape of a large, active, surface-hunting predator, and no more than that can truly be said. So do not invent the hunt. Simply understand what the body allows, a big-eyed daylight predator, working the open ground, waiting for whatever the shore brings within reach. And do not dress this animal in menace either. It is easy to look at 2 feet of scorpion and imagine a monster, but that is a story laid on from outside. What you actually have before you on this shore is calmer and stranger than any monster. It is a cool-blooded animal, moving when the warmth permits, resting through the long middle of the afternoon, breathing open air over folded tissue, watching the flats with ancient eyes. There is no theatre in it. There is only the plain competence of a body well matched to a warm, open, volcanic margin. Let the afternoon carry on around it. The heat still rises from the volcanic ground and the warmed water. The mineral crusts hold their pale shelves along the shore. Now and then the scorpion shifts, a few slow steps across the flat, a resettling of the legs, and then that long stillness returns. This is the whole shape of its day, this alternation of small movement and long waiting tuned to the temperature of the ground beneath it. Nothing here hurries, nothing here needs to. The animal simply persists, hour after warm hour on the open margin of a Scottish lake that no map will ever name in its own time. Hold the picture as the light begins to lengthen. The largest scorpion the world has yet produced stands on a warm volcanic shore, over 2 feet of patient hunter, wide-eyed in the daylight, air-breathing, unhidden, unburrowing. Roughly 340 million years will pass between this afternoon and the moment you imagine it. When people finally dig this animal from the layered rock at East Kirkton, they will find it among the fossils of a volcanic lakeshore, and inside its body they will find the book lungs that prove it had come fully onto land. From those quiet remains they will read back the whole scene you've just stood inside, the open ground, the large eyes, the absence of any burrow, the slow committed breathing of a giant that walked in the sun. And yet, for all its size, this is still a land scorpion, and a land scorpion has its ceilings. 2 feet of hunter on a warm shore is close to the largest such body the age of giant arthropods offers you here. Stand with it one more moment. Watch it settle again near the pale crust, its tail curved, its wide eyes fixed on the flat, its slow lungs working the rich open air. This is one of the largest scorpions ever to have lived, and you have spent an afternoon inside its ordinary quiet. But it is not the largest arthropod these deep ages made, not by a long measure. The truly immense ones belong to the water, and they came from a time older than this warm Scottish shore. Older even than the coal forest that will one day give this whole age its name. To meet something larger still, you have to leave this shore and travel back tens of millions of years, to a river far older than the coal forests themselves. To meet something larger still, you have to leave this shore and travel back tens of millions of years, to a river far older than the coal forests themselves. To meet something larger still, you have to leave this shore and travel back tens of millions of years, to a river far older than the coal forests themselves. Come down slowly into cool, clear, fresh water. This is the Rhineland, in what will one day be Germany, roughly 390 million years ago, the early Devonian. The tall lycopsid forests of the coal age are still tens of millions of years away from rising. The land above these waters is low and quiet, greener only in patches, nothing like the closed canopy you left behind. Here the great abundance is in the water, not on the shore, and in the water lives the largest arthropod that has ever been shown to exist. Let the river settle around you. The current moves gently over a bed of fine sediment and scattered stone. The light comes down in soft, shifting bars, filtered and greenish, dimming as the channel deepens. It is the kind of fresh water you might wade into on a warm afternoon, clear near the surface and cool against your ankles. Somewhere below that comfortable brightness, in the shadowed water near the bottom, something long is holding still. You would not see it as a shape at first. You would see the claws. Each one is a jointed, grasping limb, a chelicera tipped with opposing spined pincers. Held out ahead of the body, they reach forward into the current like a pair of barbed rakes. A single one of these claws, preserved in stone, measures about 18 inches long on its own. That is the length of your forearm from elbow to fingertip, and then a little more. It is a claw longer than most modern lobsters are, from head to tail, in their entirety, and it belonged to an animal built to a scale that matches it. This is Jaekelopterus rhenanii. When you scale the whole body to the claw, the animal stretches to somewhere near 8.2 feet in length, taller than a doorway, longer than most humans are laid end to end. A single freshwater predator, gliding through a Devonian river, roughly the length of a small car. Sit with that for a moment. The rivers of the deep past held a hunter you could not have wrapped your arms around. Now watch how it moves. The body is broad and flattened, tapering back toward a tail. Along the sides run paddle-like limbs that sweep the water in slow, deliberate strokes. It does not race. It cruises. It patrols the channel with the unhurried confidence of a thing that has no reason to hurry, because in this river almost nothing is larger than it is. The paired eyes sit forward on the head, reading the water ahead for movement, and always out in front those two long claws feel their way through the current, ready to close. You're looking at a Eurypterid, a member of an extinct group of aquatic arthropods, distant relatives of the horseshoe crabs and the arachnids that ruled ancient waters for a very long span of the Paleozoic. And here we should stop and correct something gently, because the common name for these animals has misled almost everyone who has ever heard it. Eurypterids are known, in popular language, as sea scorpions. It is a memorable name. It is also, in this case, doubly misleading, and it is worth taking the time to untangle it slowly, the way you would work a knot loose in the dark. The name conjures the open ocean and the stinging arachnid of the desert floor. Neither picture fits Jaekelopterus well. Start with the sea. Despite the name, the evidence for this particular giant points not to the ocean at all but to fresh water, to rivers and lakes. The rock that preserved it, the Wilverath deposit in the Rhineland, is freshwater strata. So the largest sea scorpion ever found was, as far as the evidence goes, not a creature of the sea. It was a river animal, a lake animal, a hunter of the same kind of clear, cool, inland water you might drink from. And the scorpion half of the name asks for care too. Jaekelopterus is not a scorpion in the way the desert animals are. It is a Eurypterid, its own ancient lineage, related to the scorpions only far back along the branching tree of the arthropods. It did not sting. Its weapons were those two enormous grasping claws, not a venomous tail. So hold the common name lightly. Sea scorpion is a label of convenience, handed down and repeated, and the science has quietly moved past it. When you picture this animal, put it in fresh water and arm it with pincers rather than a sting. What those pincers tell us is the most vivid part. They are not delicate. They are heavy, robust, and lined with spines along the grasping edges. This is not the anatomy of a filter feeder or a gentle scavenger picking at the bottom. This is the anatomy of an active predator, a hunter that reached out, seized living prey, and held it fast while it fed. In the rivers of the early Devonian, that made Jaekelopterus something close to the top of its world. The fish of that age were still armoured, still finding their form, and a grasping arthropod 8 feet long would have been among the most formidable things in the water. Imagine the moment of a strike. Not the sound of it, which no fossil can give us, but the physics. A smaller animal drifts within range. The long claws, which have been feeling ahead through the current, suddenly close. The spined edges interlock. There is no escape from a grip like that, backed by limbs the length of a human arm. The prey is drawn back toward the mouth parts beneath the head, and the river returns to stillness, its surface unbroken above. A hunter this large did not need to strike often. It needed only to strike well. Hold that scene, because now we come to the part of this animal that quietly unsettles the tidy version of the whole giant arthropod tale. You may have heard, and elsewhere in this journey you will hear, that arthropods grew to these enormous sizes because the ancient air was unusually rich in oxygen. The Carboniferous atmosphere is often estimated near 35% oxygen, against about 21% in the air you're breathing now. The reasoning goes that more oxygen let arthropod bodies, which breathe through passive tubes rather than lungs, push past their usual size limits. It is a clean and satisfying explanation, one high tide of oxygen lifting every giant at once. Jaekelopterus does not fit that clean explanation, and the reason is time. This river you are floating in, the early Devonian Rhineland, sits roughly 60 million years before the Carboniferous oxygen peak that most giant bug stories lean on. 60 million years is not a footnote. It is more time than separates you from the last of the non-bird dinosaurs. So the largest arthropod we know of was already fully grown, already patrolling its rivers at 8 feet long, tens of millions of years before that famous oxygen high tide ever arrived. It did not wait for the rich carboniferous air. It got enormous in an older, lower oxygen world. That single fact complicates everything the oxygen theory wants to say. If the biggest arthropod of all time reached its size long before the oxygen spike, then the spike cannot be the whole reason arthropods got big. It cannot even be the main reason for this one. Something else was at work in these Devonian rivers. Perhaps the water itself, which holds and delivers oxygen differently than air. Perhaps the room to grow that an aquatic body enjoys, buoyed and supported by the water around it, freed from carrying its own weight on land. Perhaps the simple absence, in these rivers, of anything large enough to stop it. The honest answer is that we do not fully know. The neat one-spike story is too small to hold this animal. That is worth remembering as you drift here. The past does not always arrange itself into a single tidy cause. The giant of the coal forests and the giant of these older rivers may have grown large for different reasons, in different worlds, breathing different air. Gigantism, it seems, was not one event with one switch. It happened more than once, and the oxygen-rich Carboniferous was only one chapter of it, not the beginning. Now, before you let this animal grow too solid in your mind, honesty asks for one more slow correction, and it is an important one. We have been describing an 8-foot predator in some detail, its cruising body, its paddling limbs, its patient hunting. But you should know exactly how much of that comes from bone-hard evidence, and how much comes from careful reconstruction, because the difference matters, and this channel would rather tell you the seams than paper over them. What was actually found in the Villereth rock was the claw, one giant chelicera, about 18 inches long. That fossil is real and solid, held in stone, measured and described. In 2007, the paleontologists Simon Braddy and Marcus Poschmann published that description in the journal Biology Letters. From that single claw, they calculated the size of the whole animal. Here is how such a calculation works. Among the Eurypterids, there are smaller, better preserved species, animals known from complete or nearly complete bodies. In those complete specimens, you can measure the ratio of claw length to total body length. You can see how large the claw is compared with the animal that carried it. Then you take the giant Wilwareth claw, apply that same ratio, and scale upward. The claw is this long, and in relatives the claw is this fraction of the body, therefore the body was about this long. That is where the figure near 8.2 feet comes from, not from a complete Jaekelopterus laid out in the rock, but from a claw and a proportion, so the full body of this giant is, in a real sense, inferred. The proportions are borrowed from better preserved cousins. No one has ever pulled a complete Jaekelopterus body from the ground and stretched a tape along the whole of it. The claw is fact. The 8-foot animal is a careful reconstruction built outward from that fact, and it rests on the assumption that this giant was built to the same proportions as its smaller relatives. Does that make the animal less real? No. The claw is genuine, and it is enormous, and a claw that size did not grow on a small body. The reconstruction is reasonable, and it is the best that the evidence allows, but it is a reconstruction, and you deserve to know that when you picture the 8-foot hunter, you are picturing a scientific inference, drawn honestly from a single spectacular bone-hard piece. The uncertainty rides along quietly beside the wonder. It does not cancel it, it simply keeps it honest. This is how much of deep time reaches us, not as whole animals, intact and obvious, but as fragments. A single claw, a single wing, a run of footprints pressed into old mud. From these pieces, patiently, the shape of a vanished world is drawn back into view. The Wilwareth claw is one of the finest of those fragments, because from it, an entire river predator can be reconstructed, and because that reconstruction reaches all the way back into a world 60 million years older than the coal age you have been walking through. So take one long look at the water before you leave it. Let the green light shift across the riverbed. Somewhere in the deeper shadow, The long claws are still feeling their way through the current. Patient and unhurried, the largest weapons any arthropod is known to have carried. This animal ruled its stretch of fresh water not because the air had grown thick with oxygen, but for reasons older and less certain than that. It was already a giant when the coal forests were still only a possibility in the far future. It was the largest of them all, and it lived in a river, and its name lied about the sea it never swam in. Feel how strange and how ordinary the setting is at once. Fresh water, cool and clear, the sort you know. And moving through it, a predator longer than you are tall, from a world so far back that even the giants of the Coal Age would have seemed to it like distant descendants not yet born. The Devonian rivers held their own age of monsters, quiet and cool and green, long before the warm swamps ever steamed. Now begin to rise slowly back up through the bars of green light toward the surface. Let the river fall away beneath you. Let those long claws sink back into the shadow and the deep past that holds them. You have gone as far back as this journey reaches, to the oldest and largest of the giants, and now the current of time turns forward again, carrying you toward the world you know better. Ahead of you, still tens of millions of years in the future from this river, the great coal forests are waiting, the tall lycopsid trees, the warm, heavy, oxygen-rich air, the armoured millipede relatives on the forest floor and broad-winged griffinflies over the wetlands. You have seen how large a hunter could grow in this older, cooler, lower oxygen water. Now you can carry that knowledge forward into the Swamp Age, where a different set of giants grew large for reasons that may or may not have been the same. The comparison is the gift this river gives you. 2 ages of enormous arthropods, separated by 60 million years, breathing different air, and each one asking the same quiet question about what really lets a body grow so large. Let that question settle in you as gently as sediment settling on a riverbed. There is no single tidy answer, and there does not need to be one tonight. The largest arthropod that ever lived was a freshwater river hunter from an older world, known to us from one long claw and a careful reconstruction. That is enough. That is a real and remarkable thing to have carried up out of the deep past and set down beside you in the dark. The water is behind you now. The green light is fading above. The rivers of the early Devonian close over their giant and grow still, the way they have stayed still for 390 million years, waiting for a claw to be lifted from stone and for the animal to be drawn, carefully and honestly, back into the light. Breathe slowly. Let your shoulders soften into the quiet. The oldest chapter of this journey is closing behind you, and the warm forests are drawing near again. Begin with the object itself, cold and specific, resting in a gloved hand. Not an animal. A single hard fragment lifted from stone, and a body that vanished before the first dinosaur drew breath. A claw, a wing, a run of armoured plates. From that one piece, a scientist must rebuild a creature no living eye has ever watched move. There is a method for this, and it has a plain name: allometry, the study of how the parts of a body scale against the whole. Start with the ordinary version of the idea, the one you already carry in your own frame. A grown human hand is not simply a baby's hand made bigger. Proportions shift as size climbs. A newborn's head is enormous next to its body. An adult's is not. Bones, limbs, and organs each grow at their own rate, and those rates can be measured, plotted, and turned into a rule. That rule is the quiet engine underneath every giant in this forest. It lets a known part predict an unknown whole. Walk through how it works when the animal is long gone. You have your fragment, and you measure it with care. Length, width, the curve of an edge, the spacing of small features. Then you find its living or fossil relatives, ones preserved as complete bodies, small enough to have survived whole in the rock. In those complete specimens, you measure the same part, and you measure the entire animal beside it. Now you have a ratio. In the small intact relatives, this claw runs a certain fraction of total body length. You assume, carefully, that the giant obeyed a similar proportion. You divide, you scale, and a whole animal appears from a single bone. Hold that logic against the most famous case in this whole high-oxygen world. In freshwater rock in the German Rhineland, roughly 390 million years old, there lies a single fossilized claw. On its own it measures about 18 inches, longer than a grown adult's forearm. It belonged to Jaekelopterus rhenaniad, a river-dwelling relative of the sea scorpions. There is no complete body, no head, no tail preserved beside it. There is only the claw and the question it forces. In 2007, Simon Braddy and Marcus Poschmann answered that question in the journal Biology Letters, and they did it with proportion, not guesswork. They gathered complete smaller eurypterids, the well-preserved cousins whose entire bodies survived in stone. In those animals, they measured how long the grasping claw ran compared to the length of the whole creature. The claw is a predictable fraction of the body, so they took the giant 18-inch claw, applied that same fraction in reverse, and let the arithmetic carry them up. The number it returned was staggering. A body around 8.2 feet long, not counting the claws that reach out ahead of it. The largest arthropod that has ever been shown to exist, rebuilt from a single grasping limb pulled out of an ancient river. Notice what just happened, because it matters for everything you have heard tonight. Nobody measured an 8-foot animal. Someone measured an 18-inch claw, and then reasoned outward with a ratio borrowed from its smaller kin. The claw is a fact you can hold. The 8-foot bod is an inference, honest and careful, but built rather than observed. The same quiet arithmetic rebuilds the giants of the air. Meganeuropsis permiana, the largest insect known to have lived, is not preserved as a complete body either. What survives is a wing, incomplete, a little over a foot long in the fragment, unearthed from red Permian mudstone in Kansas. Frank Carpenter, working through the late 1930s, took that partial wing and reconstructed the rest. Wings scale with bodies in the griffinflies and their relatives, and a reconstructed wing near 13 inches implies a wingspan reaching about 28 inches, with a body close to 17 inches from head to tail. Again, no complete animal lay in the rock. A single wing did, and the giant grew outward from it by proportion. Arthropleura offers a gentler version of the same problem, because more of it survives. The great block from the English coast held not one part but a run of articulated armoured segments, curved and overlapping like stacked tiles. When you have a stretch of the body preserved in sequence, you can measure the width of the segments and the length of the recovered run, then estimate how many segments the complete animal carried and how long the whole would stretch. That is how the figures near 8.6 feet long and about 1.8 feet wide were reached. It is still reconstruction, but it leans on far more preserved material than a lone claw ever could. And there is a second, stranger line of evidence for Arthropleura, one that skips the body almost entirely: trackways. Across ancient floodplain mud, now hardened to rock at Joggins in Nova Scotia and at El Cobre Canyon in New Mexico, run paired rows of blunt, closely spaced footprints. These trace fossils carry the name Diplycnites, and the widest attributed to this animal spread to about 20 inches across. From the width of the trackway, the spacing of the prints, and the stride, you can estimate the width and size of the animal that pressed them down, even when no piece of its body lies anywhere near. A walking creature in its walk, reconstructed from the marks its many legs left behind. This is the moment to pause and be honest with you about the seams in the method, because a careful narrator names them. Allometry is powerful, but it rests on assumptions that can bend. The first is that the giant shared its proportions with its smaller relatives. Often that holds well enough, but proportions can shift with size, and that shift is the whole point of allometry itself. A claw that runs a fifth of the body in a small animal may not run exactly a fifth in a creature many times larger. Big bodies face different physics, and their parts sometimes change shape to meet it. The second soft place is the choice of reference animal. Your scaling is only as good as the completely preserved cousin you measured against. If the reference is close kin, built on the same plan, the estimate stands on firm ground. If it is more distant, or itself a little distorted by the flattening pressure of fossilization, the ratio drifts, and every number downstream drifts with it. Choose a slightly wrong yardstick, and you rebuild a slightly wrong animal confidently. This is why serious estimates arrive wearing error bars rather than a single hard figure. When you read that Jaekelopterus reached about 8.2 feet, the word about is doing real work. The true length might have run a little under or a little over, depending on how faithfully that giant followed the proportions of its smaller relatives. The honest scientist reports a best estimate and the range around it, and resists the temptation to sand the number down to a clean certain point. A range is not weakness. It is the shape of knowledge earned by inference. Hold on to the distinction underneath all of this, because it is the quiet spine of the science. There is a fact you observe, a fact you reconstruct, and they are not the same kind of thing. The 18-inch claw is observed. You can lay a ruler along it. The 8-foot body is reconstructed, assembled from that claw by a chain of careful reasoning, each link a measured proportion in a smaller cousin. Both belong in the record, but one is read directly from the stone, and the other is inferred from it, and a trustworthy account keeps the line between them visible. So when you picture these creatures, the river giant with its grasping claws, the wide-winged hunter over the marsh, the long-armoured grazer of the forest floor, understand what you are truly seeing. You are seeing careful inference given a body. Behind each giant stands a small, complete relative that made the scaling possible, and a scientist who measured a fragment, chose a yardstick, ran the proportion, and reported the range with its uncertainty intact. The fragments are real and hard and countable. The full animals are the best supported reconstructions we can build from them, honest estimates rather than measurements taken from a living flank. That is the strange, patient gift of this work. From a single claw in German rock, from one wing in Kansas mudstone, from a run of segments and a trackway 20 inches wide, whole vanished animals are coaxed back into rough dimension. Not perfectly, not with the certainty of a creature you could weigh, but closely enough to stand them upright again in the mind, and to walk them, slowly, back into the warm and heavy air they once moved through. Now come forward again to the coal forests, into their last chapter, as the warm and heavy air begins to change. Now come forward again to the coal forests, into their last chapter, as the warm and heavy air begins to change. You are standing where you have stood before, ankle deep in warm black water. The great lycopsid trees still rise around you. Their diamond-scaled trunks climb more than 100 feet into a green ceiling, some of them near 160 feet, tall as anything the land has yet grown. But something in the light is different now. The canopy is thinner, gaps have opened where whole stands once pressed shoulder to shoulder, and through those gaps a paler, cooler sky looks down. Let this be slow. Nothing here falls in a day. What you are watching is the long turning of a world, spread across hundreds of thousands of years, so gradual that no single creature alive in the swamp could ever have felt it move. Around 305 million years ago, the climate of this planet begins to tilt away from the warm, wet steadiness that built the coal forests. The air grows cooler, the rains grow less certain, and far to the south, on the great joined landmass of Gondwana, ice begins to gather and spread. Picture that ice if you can, though you will never see it from here. Thousands of miles away across a supercontinent, glaciers thicken over land that once lay green. As that ice locks up more and more of the world's water, the seas begin to draw down. Over the long collapse, global sea level falls by something close to 330 feet. Coastlines crawl outward, shallow inland seas empty and dry. Rivers that once wandered wide across flat deltas now cut deeper, narrower channels through drying ground. You feel none of this as a catastrophe. Stand in the swamp and the water is still warm around your ankles. The peat beneath your feet is still soft and waterlogged and heavy with the smell of slow decay. That black sodden ground is the same drowned plant matter that, pressed and cooked beneath a later rock, becomes the coal seams buried under the modern world. But the water is not rising to feed it as reliably as before. Season by patient season, the drier air pulls at the edges of the wetland, and the forest, which for tens of millions of years had spread nearly unbroken across the wet tropics of Euramerica, begins to come apart. This is the event geologists call the Carboniferous Rainforest Collapse. The name sounds sudden, and it was not. What it describes is fragmentation, the breaking of one continuous living thing into scattered pieces. The great forest does not burn down in an afternoon, it splits. Where there had been an ocean of trees stretching past the horizon in every direction, there come islands of trees separated by drier ground the old swamp species could not cross. Each island is smaller than the whole. Each is cut off from the others, and on an island life has fewer places to go. Watch what that does to the trees themselves. The coal forests were built above all on the arborescent lycopsids, the giant club mosses, trees like lepidodendron with its diamond-patterned bark and sigillaria standing beside it. These were not trees as you know trees. They were towering relatives of small ground plants, grown to 50 yards and more, holding themselves up with bark rather than wood, shedding spores rather than seeds. They needed water, and plenty of it, standing close around their roots. They were exquisitely built for a drowned world. They were poorly built for a drying one. So as the wet ground shrinks, the lycopsids shrink with it. Before the collapse, the forests had held more than 100 genera of these great spore trees, a dense and varied crowd of forms. By the time you cross into the Permian, on the far side of this long turning fewer than 20 remain. Think of that number as a felling. More than 4 out of every 5 kinds of these forest giants are gone, thinned away as their swamps broke into patches and the patches dried at the edges. The cathedral does not fall all at once. Column by column, it simply stops being replaced. And this matters for the giants that flew and crawled beneath those columns, because the forest was never only trees. The forest was the whole machine that made this world possible. The dense, wet, endlessly rotting plant growth fed an atmosphere unusually rich in oxygen. A sky holding something near 35% oxygen against the roughly 21% you breathe today. That thick, oxygen-heavy air is one of the conditions most often named when people ask how the arthropods of this age grew so large. Take the forest apart, and you begin, slowly, to take that condition apart with it. You have met the giants already, in the chapters behind you. You have stood near the armoured bulk of Arthropleura, the 8-foot millipede relative that grazed this forest floor. You have watched the broad wings of Meganeura and its griffinfly kin cut over the open wetlands on spans of 2 feet and more. You have seen the scorpion and the river hunter of older, stranger worlds. Now you are watching the stage that held them begin to close, not violently, just steadily, the way a long day loses its light. But the giants do not vanish the moment the forest fragments. Life is stubborn, and the biggest of all the flyers is still ahead of you. To reach it, you must step forward across the boundary itself, out of the Carboniferous and into the early Permian, into a world already changed by the collapse behind it. Come to red rock and drier air, roughly 285 million years ago. Come to a place that, in the modern world, will be called Elmo in Kansas, and meet the largest insect that has ever lived. Its name is Meganeuropsis permiana. Say it slowly, because there will not be another like it. It is a griffinfly, a member of the order Meganeuropsis, a relative of the dragonflies you know, but not a true dragonfly itself, separated from them by a gulf of nearly 300 million years. In life it would have hung in the air over open Permian wetlands on 4 long, glassy wings, veined in a fine, dense net, a hunter of other insects taken on the wing or seized from a perch above still water. And its scale is difficult to hold in the mind, so let us build it in pieces you can feel. Hold out your arms. A single wing of this animal ran about 13 inches from base to tip, roughly the length of your own forearm from elbow to fingertips. Now set 2 of those wings out to either side and add the width of the body between them, and you reach a wingspan estimated up to 28 inches. That is more than 2 feet of insect held in the air. Reach both hands out as wide as a large serving platter, wider, and you're only beginning to frame it. From the front of its head to the tip of its long tapering abdomen, the body measured close to 17 inches, near the length of your own forearm and hand together. Nothing in the insect world has ever matched it, before or since. Every dragonfly you have watched skim a summer pond, every moth that has ever come to alight, every beetle and bee and wasp across the whole vast history of flying insects, all of them smaller than this one griffinfly hanging over a Permian marsh. It sits at the very top of insect size, the single largest to have ever left the ground. And here is the quiet, remarkable thing about how we know it. We know it from almost nothing. In the modern world in 1937, researchers lifted from the red Permian mudstone of Elmos a single fossil wing. Not a body, not a complete animal. One incomplete wing, fragile and flattened, a little over a foot of ancient membrane pressed into stone. The Harvard entomologist Frank Carpenter studied it and, in 1939, described it formally. From that one wing, and from what is known of the proportions of related griffinflies, the whole staggering creature was reconstructed. The wingspan, the body length, all of it extrapolated outward from a single incomplete piece. Let that settle, because it is worth being honest about. The 28-inch wingspan and the 17-inch body are not measurements taken off a complete fossil laid out on a table. They are careful reconstructions, built by scaling from a fragment. The fragment itself is solid, real evidence, stone you could hold in your hand. But the full animal around it is inference, a giant rebuilt from one of its own wings. When you picture Meganeuropsis in the air, picture also how thin the physical thread is that connects us to it. One wing and a great deal of patient reasoning. There is a companion to this creature, and its story is much the same. In 1940 in Oklahoma, another fragment came out of the ground, a 4-wing piece about 11 inches long. It was named Meganeuropsis americana, though many researchers now think it most likely the same animal as permiana, a second name for one kind of giant. That 11-inch fragment is held today in the Harvard Museum of Natural History resting in a case, and it carries a quiet distinction. Reconstructed to its full length, it is the largest insect wing fossil ever found. The largest single wing, from the largest insect that ever flew, preserved as a broken piece you could lay along your forearm. So the 2 greatest flyers this world ever produced are known, between them, from a handful of incomplete wings in museum drawers. No complete body, no perfect outline pressed whole into stone, just fragments, and the long, careful work of imagining the rest. This is often how the deep past reaches you, not as a finished animal, but as a single beautiful piece of one, and the humility of knowing how much you're filling in. If you are drifting now, let the drifting come. There is nothing here that needs your effort, only your quiet company as the age winds down. You do not have to remember the names, you do not have to hold the numbers. Let them move past you like slow water, and stay only with the feeling of standing at the far end of something enormous, watching its last and largest wonder hang in a cooling sky. For all its size, Meganeuropsis lived in a world already narrowing around it. The great continuous forest that had fed the high oxygen air was gone, broken into the scattered patches the collapse had left behind. Griffinflies of this scale almost certainly could not have threaded the dense interior of a crowded forest anyway. Their wings were simply too wide to clear the trunks. Instead, they belonged to open marshland and wetland sky, patrolling above still water where nothing blocked their span. As the wet places grew smaller and further apart, so did the open hunting grounds these giants needed. The largest flyer arrived, in a sense, near the closing of the room built to hold it. And it is worth pausing on why the giants were possible at all, because even that old and familiar answer is no longer settled. For a long time, the explanation went like this. Insects do not breathe with lungs. They take in air through a branching network of tiny tubes, the tracheae, that carry oxygen inward by simple diffusion, the gas seeping passively along the tubes to reach the tissues. In an ordinary atmosphere, the reasoning went, those tubes set a ceiling on size because a very large body cannot pull enough oxygen, deep enough through passive diffusion alone. Raise the oxygen in the air, as the Carboniferous did, and you loosen that limit. Bigger bodies become possible, the giants follow. It is a clean and satisfying story, and it may not be the whole truth. In recent years, the idea has been tested directly, and it has not simply passed. In a study published in 2026, a team led by Edward Snelling at the University of Pretoria examined the oxygen-delivering structures inside insect flight muscle, working from more than 1,300 detailed micrographs across 44 species, and reaching even to estimates for a griffinfly the size of Meganeuropsis. What they found ran against the old certainty. The space given over to those tiny air tubes in flight muscle did not scale strongly with body size, even in the giants. If oxygen diffusion were the hard wall on insect size, you would expect the largest bodies to devote far more of themselves to plumbing. They do not seem to, so the oxygen explanation, repeated for decades as though it were settled fact, is now genuinely in question. Other ideas share the flaw. Some researchers point to the danger of too much oxygen for insect larvae, a toxicity that might shape body size from the other direction. Others look to the plane geometry of surface and volume, the way a body's proportions constrain what it can supply to itself. The honest position, the one worth carrying with you into sleep, is that we do not fully know why these creatures grew so large, or why nothing since has matched them. The giants are certain, the reason for them is not. What is certain is the ending. As the Permian goes on, the great arthropods dwindle. The griffinflies of Meganeuropsis scale do not persist. The 8-foot forest grazers do not return. The particular combination of conditions that produced them, the drowned forests, the heavy air, whatever exact mix of causes it truly was, does not come again in the same way. And crucially, all of this happens before the dinosaurs, not alongside them, not overlapping with them. The entire age of giant arthropods rises and falls in a world that has never seen a dinosaur, and closes tens of millions of years before the first of them will walk. Hold that distance in your mind, gently, as one last measure of deep time. When you imagine the ancient past, it is easy to crowd it, to set the giant insects near the great reptiles, as though all the old wonders shared one long afternoon. They did not. Between the last of these giant flyers and the first true dinosaur lies a stretch of time longer than the one that separates the dinosaurs from you. The griffinfly over the Permian marsh belonged to an older world entirely, a world already ancient when the age of reptiles was still unimaginably far ahead. And so, the giants do not survive to meet the animals we usually name when we think of the prehistoric. They come to their close in their own time, in a world of drying swamps and cooling air and forests broken into islands. There is no single dramatic ending to point to, no one night when the last great wing folded. There is only the long narrowing, the slow loss of the wet, oxygen-rich world that had made such sizes possible. And then, at some quiet point, no fossil records exactly, the last of them. Let the size of it all soften now into something you can rest against. Pull your view back from the marsh. Rise slowly above the scattered patches of surviving forest, above the drying channels, above the pale Permian sky, until the giant griffinfly is only a glint over distant water, and then not even that. This whole age, all of it, the armoured grazer and the giant flyers and the scorpions of the old lakeshores, occupies a moment so brief against the length of the planet that in the long reckoning of the rocks it can seem almost a geological instant, a bright flare of impossible size that rose and dimmed and was gone. But it was not brief to the creatures that lived it. To the griffinfly hanging in the warm air, a single afternoon over the water was a whole life, complete and sufficient, wanting nothing of the millions of years around it. That is the strange kindness of deep time. Every vanished world was, to the things inside it, simply the world, warm and ordinary and enough. The giants did not know they were the last of anything. They only flew and hunted and settled on their perches as the light went orange over the marsh. Let their world grow dim without sorrow. Nothing here was lost so much as changed, carried forward into the coal beneath later ground, into the fragments in museum drawers, into the fine-veined wing at Elmo that let us know a giant had ever flown at all. The forests that seemed to fade away did not truly vanish. They became the black seams that would sit unseen in the rock, the pressed record of an entire living world, waiting in the dark long after the last great insect had come down for the final time. You have travelled a long way to reach this quiet edge. You have stood in the drowned forests and felt the heavy air. You have walked beside the armoured giant on the forest floor and watched the broad wings cut the wetland sky, and stood on the volcanic lakeshore and looked into older rivers still. Now you stand at the far end of it all, in the cooling Permian light, watching the largest wing the insect world would ever grow lower itself for the last time over still water. There is nothing left to reach for now. The names can go. The numbers can go. The great forest can settle back into peat and dark and the long patience of stone. Let your breath slow to match the slowing world. Let the marsh go quiet, one insect at a time, until only the water remains, holding the last of the light. You have followed these wings long enough to feel a question forming in the dark. Why so large? Why here, in this one narrow band of deep time, and almost never again? The oldest answer points to the air itself. Late in the Carboniferous, some 300 million years ago, oxygen may have risen toward 35% of the atmosphere. Tonight you breathe an air that is only about 21% oxygen. That older air was richer, heavier with the gas that feeds every muscle. And an insect does not breathe the way you do. It has no lungs, no blood to carry oxygen through its body. Instead, it relies on a branching network of tiny tubes called tracheae. Air seeps inward through them, passively, one molecule drifting after another, until it reaches the tissue that needs it. That passive drift has a reach. Oxygen can only travel so far down a narrow tube before it runs thin. In a small insect, the distances are short and the supply is easy. In a very large one, the innermost tissues sit farther from the open air, and the tubes must widen and multiply to keep them fed. For a long time, this looked like a clean and satisfying answer. Raise the oxygen, and you relax the limit. Thicken the air, and diffusion can push deeper before it fails, so a body can grow larger without starving from the inside. The high-oxygen Carboniferous seemed to hand its insects permission to become giants. It is a tidy account, and you can feel why it took hold. But tidy is not the same as proven, and in recent years the ground beneath it has begun to shift. In 2026, a study in the journal Nature went looking for the fingerprint that theory should have left behind. It was led by Edward Snelling at the University of Pretoria. If oxygen delivery truly sets the ceiling on insect size, then the largest insects should show it in their plumbing. Their flight muscles, the hungriest tissue they own, should be more densely threaded with air tubes than the muscles of small insects. So the team measured. They examined 320 micrographs of the finest branches of that system, the tracheoles, across 44 different insect species. They did not stop with living insects. They folded in an estimate for Meganeuropsis permiana itself, the largest insect ever known to fly, a griffinfly that weighed only about 1/4 of a pound despite a wingspan near 28 inches, and when they laid it all out, the expected pattern was not there. The space given over to air tubes in the flight muscle did not scale strongly with body size. The giants were not, as far as their flight muscle showed, straining any harder to breathe than the small ones. That is a quiet result, but it lands hard. If the largest flyers were not running out of tracheal room, then oxygen supply may not have been the wall holding insect size down. The wall everyone kept pointing at may have stood somewhere else all along. The authors did not claim to have solved it. They pried the question back open. So if not oxygen, then what? This is where you should let the certainty go soft, because no one yet holds the finished answer. One idea moves the danger to a different stage of life. It is not the adult that struggles, on this view, but the young. Researchers such as Wilco Verbeek have suggested that in very oxygen-rich air, insect larvae, especially those developing in water, face a risk of oxygen toxicity. Too much oxygen can damage tissue. A larva cannot always turn the flood off, so the pressure to survive that rich air may have shaped body size from the bottom up, through the vulnerable young rather than the adult gasping for one more molecule. A second idea is plainer, and it is about shape. As a body grows, its volume climbs faster than its surface. The inside swells away from the outside. For an animal that trades gas across its surface, that widening gap between what the interior demands and what the skin can supply becomes its own kind of limit, whether or not the outside air is rich. Surface against volume, the plain arithmetic of being large. And then there is a creature you have already met waiting in the record like a stone set in the path of the simple story. Jaekelopterus renaniae, the freshwater sea scorpion, known from a single claw 18 inches long, scaled up to a body reckoned near 8 feet. It lived about 390 million years ago, in the early Devonian. That is roughly 60 million years before the Carboniferous oxygen peak that most giant arthropod stories lean on. Sit with that gap for a moment. Here is one of the largest arthropods that ever lived, already enormous, already sweeping through Devonian rivers, tens of millions of years before the oxygen supposedly climbed high enough to allow it. If a single oxygen spike were the whole reason for giant arthropods, Jaekelopterus should not exist when it does. Yet there it is, dating from an older, thinner-aired world. It does not overturn the oxygen idea by itself, but it will not fit neatly inside it either, and honest science leaves that discomfort on the table rather than tidying it away. None of this makes the oxygen theory wrong. The high oxygen was real, and it surely mattered in ways still being untangled. What has changed is the confidence. What once sounded like an answer now sounds like one voice in an open argument, and the argument is not finished. You are listening to a question that is still being asked. There is a second riddle folded into these swamps, worth turning over before the forest goes quiet. Not why the animals grew large, but why the ground held so much carbon. The Carboniferous is named for coal, vast seams of it, laid down across those 100 million years in quantities the world has rarely matched since. Something let dead plants pile up and lock their carbon into rock instead of rotting cleanly back into the air. For a long time, a neat explanation circulated. The trees of the coal forests were built with lignin, the tough compound that stiffens wood. And in this telling, the fungi that break lignin down had not yet evolved the trick, so when a lycopsid tree fell, nothing could fully digest it. The wood simply accumulated generation upon fallen generation until it compressed into coal, a gap in the world's decay, held open until the fungi caught up. It is a memorable idea, and you will still hear it repeated, but in 2016 a study in the Proceedings of the National Academy of Sciences, led by Nelson and colleagues, pushed back on it hard. When they looked closely, lignin was not the dominant material in most Carboniferous coal, and the evidence suggested lignin decay was already happening, that the fungal machinery was not simply absent, waiting to arrive. If the wood was already being broken down, then a fungal delay could not carry the whole weight of all that buried carbon. So they pointed elsewhere, not to biology alone, but to the shape of the planet at the time. This was the age of Pangaea, the continents crowding together, and with them came the right combination of climate and geography. Wet lowland basins sitting at the right latitudes, sinking steadily so that dead plant matter was buried fast and sealed off before it could fully break down. Tectonics and climate on this reading built the coal, by opening enormous waterlogged graveyards at the very moment the great forests were shedding their mass into them. Which of these carries the truer weight is still debated. The fungal story has not vanished from popular telling, even as the evidence has moved beneath it. And that is the honest shape of this whole chapter. Two of its grandest facts, the size of the animals and the depth of the coal, both once had clean, confident answers, and both answers have since been questioned by careful work with the actual rock and the actual tissue. You do not have to resolve any of it tonight. There is a strange comfort in that. The giants were real. The wings near 28 inches across were real. The coal is real too, buried in seams laid down across 100 million years. What stays uncertain is only the why, and the why can wait. Researchers will keep measuring micrographs and splitting open concretions and scaling single claws into whole bodies, patient across their own careers, and the picture will keep sharpening long after you have drifted off. For now, let the arguments settle like ash into still water. Let the forest close over them. The oxygen may have mattered, or mattered less than we long believed. The fungi may have lagged, or the slow continents may have done the quiet work instead. The great wings do not need the answer to keep beating over the warm green dark, and neither do you. After the last of the great wings settles and grows still, the world falls quieter, and now, slowly, so will you. After the last of the great wings settles and grows still, the world falls quieter, and now, slowly, so will you. Let the scene widen, let it lift. Rise a little way above the coal swamp, just enough to see the whole of it. The lycopsid trees stand below you, 30 to 50 feet and higher, their trunks patterned in diamond scars like a texture you could run a hand across. The air is warm and heavy and green. It holds close to 35% oxygen, far more than the roughly 21% you breathe tonight. That thick, rich air is already loosening its grip, softening from fact into something you only feel. Down among the roots, the great armoured grazer is still. Arthropleura, the largest land invertebrate ever known, 8.5 feet of overlapping plates, no longer moving through the leaf litter. Let it go. Let it recede into the wet floor of the forest, its many short legs quiet, its stalked eyes closed to you now. It was never the monster old stories made it, a slow eater of fallen things drifting through decay. Watch it grow small beneath you, one long shadow among the ferns, and then no shadow at all, higher now. The canopy closes over that world like a lid, and the giants beneath it blur into the general green. Out over the open wetlands, the last of the griffinflies rests on a reed. Meganeura, whose wings spanned more than 2 feet, named by a careful hand in 1885 for the dense lacework of veins across them. You have watched it patrol the marsh all evening. Now it is only a stillness on a stem, folding into the reeds as the reeds fold into the water folds into the wide grey sheet of the marsh. Rise until the marsh is a pale seam in a darkening land. The great insect does not follow. It stays where it belongs, 300 million years down. Let your breath slow to match the lifting view. There is nothing left to chase here. Everything below you has already happened, and happened well, and will keep. Turn, and the volcanic lakeshore drifts by beneath you. East Kirkton, in what would one day be Scotland, its ground warm with hot springs, its water rimmed with pale mineral crust. Somewhere along that shore the scorpion hunted, Pulmonoscorpius, near 28 inches long, the size of a house cat and built for open air. Its book lungs were the quiet proof that it had left the water for good. You do not need to find it now. Let the lakeshore go soft, its edges smoking gently, its hunter tucked somewhere in the dark stones. The whole warm basin sinks away below the climbing view. Farther back still, and deeper down, 60 million years deeper, to a cool, clear river in the early Devonian, older than every giant you met tonight. There the sea scorpion swam that was never truly a creature of the sea. Jaekelopterus, scaled from a single 18-inch claw to a body near 8 feet long, a grasping hunter in fresh water. Its rivers ran under a leaner sky, with far less oxygen than the coal forest would ever hold. It reminds you, softly, that the world never told just one simple story about why these animals grew so large. Let that puzzle rest unsolved. It is a good thing to carry into sleep, a question with no sharp edges. The river narrows to a thread of silver and is gone. Now the whole of it lies below you at once. Coal swamp and wetland, volcanic shore and Devonian river, all the giants laid down in their proper layers of time, more than 100 million years of it, and every last one of these creatures already ancient before the first dinosaur ever set a foot on the earth. That is the shape of the thing you have been resting inside tonight. Not a single age, but a long, slow procession, arthropods rising to sizes never seen before them and never matched since. Before I let the room go dark, one small thing, offered gently and then set aside. If these quiet walks through deep time help you sleep, you can follow or subscribe wherever you are listening, on Spotify, on YouTube, or in your podcast app of choice. That is all. Nothing more is asked of you tonight. Rise again. The layers of time thin out below you into bands of soft colour, the greens and greys and warm dark browns of 100 million years pressed close. The armoured grazer, the 2-foot wings, the air-breathing scorpion, the river hunter, all of them settling now into the same still ground, the same deep quiet. One by one they dim, not gone, only resting, exactly where the rock has kept them, waiting without impatience for nothing in particular. The coal forests themselves are going dark beneath you. In time their warm wet world would cool and dry, the great lycopsid trees thinning from the swamps themselves compacting slowly into seams of coal. The last and largest of the flying giants, Meganeuropsis, with wings that reached perhaps 28 inches across, would trace the closing of that long chapter. The giants would fade away, not in a single night, but across ages too slow to feel. You do not have to watch them fade away. You only have to let them grow quiet, and they already have. The forest is a smudge of green now, far below and far behind. The rich, thick air, the crackle of distant wildfire, the smell of peat and rot and rain, all of it thinning as you climb, until it is less a place than a warmth you remember. Deep time turns beneath you like a slow dark tide, unhurried, patient, indifferent in the kindest possible way. It asks nothing, it only keeps. Higher still, and the whole prehistoric world folds shut like a book set gently on a shelf. The numbers loosen their hold, the dates, the wingspans, the long Latin names, all of them drifting off like warmth rising from the ground at dusk. You do not need to hold any of them now. They will be here tomorrow, unchanged, waiting in the rock. Let them go the way you let a long day go. And now the dark that gathers is no longer the dark of the ancient forest. It is the dark of your own room. The deep time you have been travelling pulls back and back until it is only a quiet behind your eyes. The bed beneath you, the weight of the blankets, the soft, ordinary sounds of the room settling around you. Take one slow, deep breath, the kind that fills you and then eases out on its own. Let your shoulders drop. Let your jaw soften. There is nothing left to follow, no creature to keep in view, no fact to hold. The forests have gone dark. The giants are at rest in their stone. The long procession of deep time carries on without needing you awake to witness it. Your breathing is slower now. The room is quiet. Somewhere impossibly far below, 300 million years down, a warm green world holds perfectly still and holds you with it and asks only that you rest. That is all it ever asked. To be walked through slowly and then left in peace. Let the quiet settle over the whole of it. The armoured giant in its leaf litter, the great wings folded on the reeds, the scorpion in the warm stones, the hunter in the cool river, all of it dark now, all of it kept, all of it perfectly still. And you, here, in the last soft light before sleep, breathing slow, sinking gently down toward the same deep quiet. Rest now. The ancient world will keep without you. Sleep well tonight, traveller. Good night.